Good morning to you all. On behalf of the organizing committee, I would like to welcome you all to this great meeting on complex systems, and also to celebrate the 80th birthday of this gentleman in front of me. His abilities, skills as a scientist, I will not try to mention here. We'll see some of them during this week, but he has another very important quality, which is the capacity to make friends. He makes friends very easily. So this is reflected here in this meeting, where we see many old friends, not so old, but also new friends. All of them in some way related to Constantino. Please, we would like to make you feel yourself at home. CBPF this week is your home. The organizing committee and our staff, our secretaries, Beth and Anna, and also Almério. Many of you know Almério. Almério is also known as Almério the bird, because he can whistle just like a bird. If you want to learn to whistle just like a bird, ask Almério. Then Almério can solve problems here in CBPF for you and also outside CBPF. So everywhere. So please, if you need something, please let us know, and we try to solve all your difficulties. The director of CBPF is unable to be here, but he is represented by the vice director, which is João Paulo, who will do his greetings to all of you. Please, João Paulo.
Hello to all. Thank you, Fernando, for the introduction, and thank you all for being here, ladies and gentlemen, distinguished guests, friends, and old colleagues. No? Well, it's my profound honor as the Deputy Director of CBPF to welcome you to the Statistical Mechanics for Complexity, a celebration of the 80th birth of Constantino Tsallis. Here at CBPF, as Fernando mentioned, your home for a few days. We are here to embark, you are here most probably, to embark on a scientific odyssey exploring the vanguard of statistical mechanics and complex systems. However, this conference holds a deeper significance also to come together to honor the luminary in the field of statistical physics, Professor Tsallis, as he reaches the milestone of his 80th birth. Congratulations. Yesterday, actually. As you know, Professor Tsallis' odyssey from Athens, passing through the avenues of France, Argentina, and finally coming to Brazil, where he became a citizen of our country. It's a tale of intellectual fervor. Sorry, I'm a little bit shaking here. Let me put it here, because then I can read it better. Professor Tsallis' odyssey from the historic Athens through the academic avenues of Argentina and France, and finally as a citizen of Brazil, is a tale of intellectual fervor and boundless curiosity. His work, from the theory of phase transitions to the pioneer of Tsallis statistics, has become a cornerstone of contemporary science, reaching across disciplines, of forever altering our approach to understanding the world around us. In Rio, he became a pivotal figure fostering research groups in statistical physics and making groundbreaking contributions to this that span over critical phenomena, biogenesis, cellular automata, and far beyond. His work has been a guiding star in fields as diverse as economics, cognitive, psychological, and genetics. So as we delved into the complexity of statistical mechanics and complex systems, we also take a moment to reflect on this remarkable journey of a man who has become one of the most influential physicists of our time, according to the recent Stanford list of most prominent scientists, and stands as the most prominent physicist of Brazil. Professor Tsallis, your achievements are exemplified not only in your scholarly publications and global recognition of your work with citation that numbers the thousands, but also in the lives of those who have touched your teachings, your mentorship, and your passion for discovery. In recognition of his paragon as a scientific inquirer, we also are very proud to announce that CBPF is expanding its staff with the opening of 36 positions for researchers and 10 positions for technologists. Those roles will span diverse fields, including statistical complex systems, offering a new generation of scientists to contribute to the vibrant and even evolving fields. All the information about these positions are on our website. The inscriptions for the whole process will begin in the middle of December, and the whole process will be held at the beginning, the first semester of next year. So we invite you all to invite the ones who can and will be interested to join the staff of CBPF soon. And I hope this will be a great event for us as well in complex system and so on. So with that, I warmly invite you all to proceed with the conference, inspire and eager to explore the vast landscape of statistical mechanics and complex systems. Unfortunately, I will not be able to stay here at the conference with you because I have some duties to perform for the positions that are open. We have some important meetings to celebrate some contracts and so on. But let the conference begin and welcome you all. Enjoy Rio, enjoy CBPF, and enjoy your friendship. Enjoy the collaboration among you. Okay? Thank you.
Thank you, João Paulo. We can start a little bit earlier, or we wait for 10 minutes? We wait so that you can talk with your friends for 10 minutes. 10 minutes, okay? All right. É isso. A gente tem que cumprir os horários certinho, viu? Vem cá. Evaldo, tem que checar com o cara sempre, ver se ele já está filmando, né? Agora você vai ser filmado, hein? Vai ficar para a eternidade. Okay, then we start our session with Professor José Soares Andrade from Ceará. Please.
Hello. Opa. Very good. So, good morning to everybody. Thanks a lot for the organizers. It's a real pleasure and honor to be here in honor of this nice conference of the birthday of this friend of us, as Fernando said very nicely, a person who knows how to make friends and much more things than that. So I'll try to talk about Constantino in the first 10 minutes of my talk. And then the remaining, I will try to talk a little bit about physics, but let's see. So the title of the talk is just a formality for the last 10 minutes or 15. A maximum entropy model for the network of commercial transactions between cities based on data from electronic invoices. So this mixture of science, data science and statistical physics. So you'll see what I'm going to talk about. So I come from Fortaleza, Ceará, Brazil, in the north of Brazil, for those who do not know. So I decided to I like to do subtitles. So the subtitle is this one, Introducing Tsallis 8.0. The latest upgrade in scientific brilliance. So unfortunately, this was an idea of mine, but the construction of the title itself was not mine. So I decided to ask a friend called ChatGPT-4 to produce a title with this joke, yes. And this is the talk I had, that's fantastic. A friend of mine, this is my question, a friend of mine who is a brilliant and very famous scientist, is turning 8 years old. I will be giving a talk in his honor. His name is Tsallis. I would like to make a joke using his name as it is where the name of a software in its 8th version. For example, Tsallis 8.0 something. What could be a possible title for my talk that announces the release of this software? So he said, look, it's fantastic. You know, how delightful to blend humor with honor for your friend's milestone. Given his name and the context, you could title your talk with a playful twist on software versioning. So he more than the title, he offered me suggestions for the talk itself. So, and then he, that blends scientific aspects of the software release team. So he gave me the title, which I'm using. And then within your talk, you could continue this metaphor by highlighting his new features of Constantino in the 8th version. Such as wisdom, which everybody knows, experience, contributions to science over the year, bug fixes. So this is very tough, very tough. To fix a bug of Constantino is going to be very tough. Anyway, this light-hearted approach, so it was very nice. I'm very proud of chatting with this friend of mine to obtain the title. So this is the group from which I work with. We have a lab there in Fortaleza. We now have the honor to have Professor Herman now. He's doing his, I was telling some people here, he's doing now, since he's retired from ETH in Zurich, as well as from ESPCI in France, he's now doing the Rubinstein tour. No, I call Fortaleza, Rio de Janeiro, and Paris. That's where he lives now. Helena's Rubinstein tour, so that's what people say. So I have some friends that collaborated with me, André Moreira, Humberto Carmona, Cesar, Saulo, and Deborah, and Hilder. They are all part of the work I'm going to present here. But before that, I would like to talk a little bit more about Constantino. So there was 10 years ago when he made 70. I was here. And the talk I gave was no locality in complex systems. And I decided to talk a little bit about black holes in the full context. And I knew that Constantino was working very hard on this topic, trying to develop a new thermodynamics of this very important phenomena. So at that point, I decided to make a joke, which I'm going to repeat here. And he published this paper, which apparently was contradicting the paper of Stephen Hawking. Just for you to know the level of the complexity of the problem that he was creating at that time. You know? So, and then I decided to make, apparently Stephen Hawking, who gave a seminar in England, and he didn't appear, something like that. Probably he was not so happy about this paper of yours. And then I asked a friend of mine to make. So this is Constantino with a balloon, which is a black hole with a lollipop of Q. And Stephen Hawking was so mad that he stood up from his wheelchair. Anyway, so I would like to say about something about our contributions to this field. Everything started with order superconductors. I worked on this field with Stefano Zappetti in 2001, 22 years ago. And at that time, we found out that it's possible to describe from a coarse grain, from molecular dynamics to a coarse grain description of the system on the movement, on the dynamics of superconductors, of vortices in superconductors in terms of a nonlinear diffusion equation, which has a drift term. And at that particular point, we were trying to describe as well pinning forces which might attract the vortex and keep them stuck, as well as a thermal fluctuation term. So eventually, in 2010, so together with Evaldo and Fernando and me, Andrea, and George, a PhD student of us, we found out that there is a very close connection between that description and using the maximum entropy principle. We managed to define that it's possible to identify the thermodynamics, the thermostatistics that's capable to describe the system is based on a mixture of two thermodynamics, Boltzmann and Constantino. That was our discovery. If we still, of course, keep the temperature different from zero, so you have to make it. But if the temperature is equal to zero, okay, so you can find out that the thermostatistics is perfectly described by Constantino entropy, like Tsallis non-extensive entropy. And then as you increase the temperature, you go gradually from Tsallis entropy to Boltzmann entropy. So, but you have something in the middle, which we found out analytically as well, that it can be described by functions of Lambert that I didn't know about at that time, of course. And then we found out that Boltzmann plus Constantino is equal to Lambert. But this plus is not correct, so I decided to make it plus Q. Anyway, so now I would like to go to non-extensive statistics and complex networks. So I have to make a joke. I knew he was here. So this is our last, most recent production on trying to contribute to this marvelous field, which is non-extensive thermodynamics. I've been working a little bit on complex networks, but I knew already, inspired by many works, including some of Constantino, which is all in all of them, and this force, a real force of nature, which is those who know him will understand exactly what I'm talking about. So Luciano da Silva, which I'm wondering, I don't know where he took his picture. It's fantastic, but anyway. And then what we did was very recently, instead of going from dynamical and growth models, which have some phenomenological insight, some of them are based on the dynamics previously described or in preferential growth dynamics, if you wish. But we decided to do it from using the configurational model. And in this case, we can generate what I call random unbiased complex networks. They come from the distribution of Tsallis ad hoc, in an ad hoc way. So we plug the distribution, we obtain the type of network that we want. So with this additional degree of freedom, we found a plethora, let's put it like that, of possible, flexible, and flexible features of these networks in terms of topological and transport properties, like assortativity, small word network, and resilience to random and malicious attacks. It's a very interesting network. I can tell you, it's interesting to say, I'm not sure, but maybe this is the first paper of Hans in non-extensive thermodynamics, if I may say. The second, oh my God. Anyway, based on that, I would like to finish my contribution to this. And I think the fact that Constantino is here, I know him for 25 years when I was doing my PhD here in Rio, but not in CBPF. And I came here to visit and I saw this guy. He was already very famous. And I was very inspired about his talk when he gave it 1 year later. I found, oh my God, this is amazing, very interesting. And I think he's doing everything on this. So as I'm finishing the complex networks, I decided to make something to more elaborated. I asked this artist friend of mine, and we had a conception. And this is the conception. So as you can see, it's profound. Come on, it's too left, but it's profound. So from the network, there is this hominidue there that Constantino, with his touch, is trying to pick up from the complex network, which is background involving it. Okay. So and then I would say tu engigui tau Tsallis. Tu engigui tau Tsallis, which means the touch of Tsallis in Greek. So I had to learn some Greek. So of course, this is inspired on the Michelangelo, the creation of Adam. The touch of Tsallis. I cannot create the creation of Adam again. So, o toque de Deus. No caso é o toque de Deus. So this should be the touch of God, but I put the touch of Tsallis. Okay. So anyway, this is a creation. So the graph I had to give, so since it is recorded, I have to give credits to everybody, especially the network which is behind. And that's it. Thank you very much for this. Now I go to the something completely different. So this is Monty Python. And then I go to talk about a little bit about the project chief scientist of data. I didn't translate that, I forgot. But this is a fiscal note that people, the companies, when they trade to each other in Brazil, they have to exchange. So this is the formal document between companies when they sell or buy something to another company. Okay, so it has more than 43 fields that you can use. You know, for instance, you know the company which emitted. You know the company who bought. You know the geolocalization, where did it come from, and you know the value, the type of product, the names, and everything. So we had data from that from 2010 and 2020. More than 6 billion invoices with 43 fields each. So this is the type of document that we have. So we, for instance, we decided to make this movie just to show you in a period from 2019 and 2020. So we wanted to understand the movement of these fiscal nodes in the state of Ceará to give us some ideas, some insight on the economical microdynamics of that. Okay, so I'm going very slowly. No, Fernando, I'm okay? Yeah. Yeah. Okay. So this is more or less what happens. Here you can show the total volume in millions of reals, not in millions of dollars, please. But that's how it evolves. Here is Fortaleza, the capital of the Ceará state, which is in the nose of Brazil, for those who don't know. And most of the transactions of the product trades between municipalities or cities, if you wish, come from Fortaleza in this metropolitan region, which is surrounding here. As you can see here, eventually the pandemics will start, and you will be able to see decay. Now it's the pandemic. You see that there is this famous V of someone that I don't want to say the word here, the name here, but and eventually it goes up. So our idea was to use this database and try to make some analogy with thermostatistics. Okay. So what did we do? For the first thing that we did was, okay, the Ceará state is highly heterogeneous. You have this metropolitan zone that I just talked to you about, but you have also the interior, which is very poor. It's the northeast. It's a northeast state. So due to this heterogeneity, it would be important for the purpose of the approach that we wanted to apply to calculate financial macro regions of that. So for that, we used complex networks strategies to calculate modules. Okay, so the first thing, okay, we wanted to do is to divide the state in different modules or different financial microregions, as I said. So we used, to start with, a generalized modularity algorithm, the one which is proposed, very famous one, proposed by Peixoto in 2018. It's called the stochastic block model. And the algorithm, it identifies modules based on the correlations between pairs of sites and on the network generation process itself. Then by the network, I mean the network between cities. The cities are the sites of the network, and the connections of the cities can be anything. For instance, the number of transactions that a city did for a given period of time, for a time window, okay? And then, we give all these weights. It's a directed graph. You give the connections, the weights of the graph. When the transaction is from a buyer to a seller, it has a direction, which is from the seller to the buyer, okay? And so on and so forth. You give an input, so that's what you get. This is the modules that you get for communities which according to their trades, to their number of transactions in the CRI state. So, of course, this is not so nice because you have a lot of holes in macro regions. They are not well mixed. Some of them are separated from each other in different zones. So, of course, this type of community or module way of finding the macro regions is not the adequate one. Why? Because it has nothing to do with the dynamics of the process itself. So we decided to use a different technique, which was proposed by other people. And the technique is the InfoMap algorithm, which was proposed by Ross-Paul and Bergson in 2008. This is basically relying on the transport properties which are inside of the networks. In our case, the network of transactions. So the algorithm finds modules in the network by minimizing the length of a random walker's movement. So it has this analogy with a random walk. So the network, it will be compacted if regions are identified where the walker tends to remain for a long time. So if it gets stuck in some region, so most likely these regions in which it was stuck will belong to the same module. So it will all depend on the flow of transactions that comes from one place to another. So and therefore it captures the network optimal community in terms of the flow dynamics inside of this. So we use this, we gave exactly the same input to this algorithm, and what we found was this one here. Okay, so this is a much nicer macro-region distinction between municipalities in the CRI state. Why? Because it is, I discovered, it's a simply connected module in the sense that there are no holes, and they form a single piece with well-delimited boundaries. So we thought, okay, it makes sense. Perhaps this is the best way to divide the financial communities in the CRI state. Okay, so this was the first time of our work. We are very happy about that. And then we went out to another thing. So now we have to go to thermostatistics. Okay, let's see how can we do that. So again, this is the matrix of commercial transactions when you put the cities ordered against according to the communities that they belong to. Okay, this first square here is the first community. The second one here is the second. These are the cities and the cities here, and how do they correlate to each other in terms of the transactions between one city and the other. So as you can see, for instance, Fortaleza has a very long correlation in terms of transactions with almost all cities, all municipalities in the state. So that's why you can see this very long line for Fortaleza here, going not only for buying, but as well as for selling. Okay. And of course, we see that there are strong correlations within the community. This is easy to see, you know. Apart from the fact that these very, very high and very rich cities, they extend all over the system to other cities belonging to different communities. So, and then we wanted to give away some monetization. So this has been something which has been used in complex economic complexity. People try to create bipartite networks of cities and the traded products. So now we want to know for each city what is the most important product in terms of selling or buying. And then we want to rank that for different cities as well. So it's a different, totally different approach. Instead of talking about finance, we go to talk about economy. Because we're talking about money being traded between one point to the other. Now we want to know about the importance of the product to the selling or to the buying of that city to other cities. Okay, so that's what we do. QM of P is the monetary value traded by the CTM to the product, according of the product P. So it's how the city actually sells or buy that particular product P. And RCA is revealed comparative advantage. This was created by Hidalgo in a Science of 2006. It's a very famous paper. So they decided to use this thing here, this factor here, this fraction here, which somehow tells you if RCA of P of M of the product P related to the city M, to the municipality M, is larger than 1. It means that the product P is relatively more important to trade of the city M than the relative importance of all trades of this product by all cities. Okay? If RCA for that municipality according to that product P. So in a way, you have a threshold to define whether a city is a buyer or a seller of that product. Okay, so it is a demonetized index. So in this way, what you can do, you can binarize the city product matrices. 5 minutes, okay. 5 minutes, yeah. So instead of using the RCA, what do you do here? If RCA is larger than 1, you simply binarize, and then you create something more simple, which is the activity of the city with relation to the product P. Okay. So, and that's what you get for buying and for selling. So these are the municipalities, these are the products for buying. So if you have a blue, it means that you have a -1, you have a +1. If you have a white place there, you have a -1. Okay, so as you can see, the buying is more dense than the selling. This is respected to. This comes from the fact that the cities all have basically all needs in terms of the population. But what they sell is different from that. They sell very particular products. They trade very particular products. It depends on their culture. It depends on their land and things like that. So this is why the buying is more dense than the selling. So you have different systems that you have to analyze in a statistical way different. So now we want to go to the maximum entropy model. So we are using this technique developed by Bialek and collaborators in 2006. So now you take one community, the first one here, take just that one, and then what you see here, okay, you can define M, okay, which is the municipality, as a spin. M is a spin, okay, and P is the product. P is the product. So P for a given P, you have a given configuration of the system, a state of the system, if you select a given value of P. So you have a set of P configuration of large P products that will be realizations of your system, different configurations that you get from real data. Okay, it's like you are doing a configuration of your Ising-like model for different, doing a Monte Carlo simulation. So you have to make many realizations of that, but this is real data, okay? But of course, now you can analyze in a different way. Instead of doing this, you can select a given spin and look for the variation in time. Let's put P as a time in this particular case, or in the realization, and calculate some average activity, some average magnetization of that. Okay, so this is different. So look, this is state. This is an average of the dynamics of the system for a given value of the municipality. And now you start doing the technique. So in this particular, so we have to define the constraints. It's slightly different. So our observables correspond to the average activity for a given municipality, and as well pairwise correlations for the M cities, large M, over all P products. So you have two constraints here that you know before applying the principle of maximum entropy. So you know the averages from real data, and you know the correlations from real data because you actually measure them. So you can say that you know this and you know that. So now, as I said to you, you can denote sigma in the set of sigma as the state of the system of the M cities passing through the product P. So these are two different things to know. And now, of course, since every city is one of two states overall, you have 2 of n possible configurations of that system that it can assume for each product. So now it's possible to show, I'm not going to be here. Fernando fortunately said that I have only 5 minutes, so I will not be able to do that. But it's possible to show that using these two constraints here, using this constraint here, the normalization one, and knowing that the entropy can be described in this one, so it's possible to show that the model which captures the physics of this, not the physics, the mathematics of that, so to reproduce real data is compatible exactly with the Ising model. In a first approximation, it has the most structure to capture all the data that you need, that you observed from data, and this is what I call Ising model from real data. Okay. So this is not a metaphor in the sense that we are not postulating the underlying dynamics of the system. It's possible to obtain it from the constraints of your real data, that the Ising model is the simplest structural model that you can use to capture the entire system with the less information that you have. Okay, so you can do that. We assume that beta is equal to 1. Now you know what temperature in which you are working for that particular system. And then what we want now is to recover what are the couplings and the local fields. So of this Ising model Hamiltonian. So this is also called in literature of computational data, Boltzmann machine learning. So I have to tell you now, we are working on the Tsallis machine learning. We have preliminary results now. I need to talk. So it's possible in practical terms. What we do, we try to minimize the distance between what we have from real data, updating the couplings as well as the local fields for each spin, for each municipality, so that you are able to recover these parameters from observables. So once you do that, you can infer the sets of HM and the sets of JMN that better reproduces the real data that we have, while you maximize the entropy, and then the Boltzmann distribution will perfectly characterize the product activities of the cities composing a given community. So this is my almost the last slide. So once you do that, you have assumed that for that particular moment, the temperature of the system is arbitrarily set to 1. So once you have the couplings and the local fields, now you can change the temperature of the system using for instance, you can calculate the heat capacity, the specific heat for different temperatures by simply changing the temperature in your machine. So once you do that, you can see, for instance, how the heat, the specific heat changes with temperature, and you can see that for different communities, all of them, either for buying or for selling, are very close to the somehow a critical point, which is the maximum of the specific heat for this curve against T. So it shows a peak which is similar, which is analogous to a critical point. So in a way, what we observe is that the system is close to the critical point, but subcritical. So the consequences of that for our audience of phase transition that we have here is that, for instance, we have to explain some sort of cohesiveness between the cities and the degree of extension. And of course, it's a good idea to remember the principles proposed by Pierre Bach in terms of self-organized criticality. The complex behavior in nature reflects the tendency of large systems to evolve into a poised critical state, way out of balance. Perhaps the economical trade way of cities can be in a sort of self-organized criticality state. Okay, so I have more things here. The state established, this was the theory of Pierre Bach. So without fine-tuning, it should go to criticality by itself. So thanks very much again. Thanks a lot, and happy birthday, Constantino.
Okay, we have time for some questions. Eugenio.
Thank you, Fernando. Thank you for the nice talk with lots of humor, actually. When you, almost at the beginning of your presentation, you kind of grouped the areas, and you were simplifying this geographical description. And my question, and because in some of you, eventually we could look at it, and in one of them, you organize in such a way that some of these small municipalities, I guess, were left out of your consideration. They didn't seem to be included.
But in which algorithm are you asking for? Because there is the algorithm which only arranged everything 5 modules.
Right. It was about the second one. And the question is, was there a tolerance for the amount of these municipalities that were left out of the analysis?
Yeah, the algorithm itself has several criteria that you have to tune to find out which one is the optimal. But of course, this is a numerical. Yeah, there is a point in which I have a couple of parameters, and you have to test them yourself in order to obtain results that you think are consistent. This is based on.
Just time for one more question.
What about the 3-point correlation?
No, I didn't have time to show you. So, but this is a very important question, of course. Yes. I don't have it here, but of course, when you do this inference of the couplings and the local fields, you have to prove that you reached convergence of your technique, of your machine Boltzmann analysis. The first convergence test is the fact that the activity itself, the average activity, as well as the correlations, will fit from the observation itself, as well as from the model. So this is perfect, But there is one which is not implicit in the Ising model itself, which is the 3-point correlation. So the 3-point correlation is kind of final test for the convergence of your technique, whether it represents or not. Because even if it's not there in the Ising, you have it. It's not explicit in the Hamiltonian, but if you measure it, you might have it depending on the configuration of parameters that you have. So this is the question of Hans. I have it here. They are very good.
Okay, let's then thank José.
Nervoso. Passou muito.
Pouco só. I think. Oh, Evaldo.
You should put it over there. I don't know.
But you only want the point,
Yes, but also to move the.
I don't do that.
I need something to move the.
Ana, não tem apontador, não? Não.
Well, maybe I can stay here.
Evaldo.
Fernando, if I stay here, can I use the mouse?
Apontador.
Sì, ma ce l'ho, ma si deve mettere da qualche parte.
We forgot the most elementary thing, a pointer. Oh,
Does it work?
Previous, next, with pointer.
Okay.
You press the button for.
This is to move.
okay. So the next speaker is Andrea Rapsarda from Italy, Catania. This is an old friend of Constantino.
So, good morning, everybody. Thank you to the organizer for having me here, and it's for me a great pleasure to be here again. As a matter of fact, I was here for your 60s, for your 70s, and now for your 80s. And hope to be here again in the future. So my talk will be a recollection of memories of our long-standing collaboration, both from a scientific point of view, but also from a kind of memories of our collaboration, which is 25 years old. So, let's see. So everything started with this paper. This paper, in collaboration with Vito Latora and Stefano Ruffo, was published in '98. Vito was at MIT at the time, and I was going there visiting him. And we were very much interested in this kind of system, since it reproduced in a nice way a system which had a kinetic part, but also a second-order phase transition, because we were interested in second-order phase transition in finite systems. And this is the system. It is the famous Hamiltonian mean field model, which was introduced by Stefano. And the system has an infinite range force, and it's a useful pragmatic model for many real systems, from astrophysics to fragmenting nuclei or atomic clusters. And here is the model. It's very simple. It has a critical point and shows a second-order phase transition. I go fast here because I think that everybody here knows this model. It has, of course, the critical exponents of a mean field model at equilibrium, of course. And we were interested at that time to see if a finite size system could show evidence of a thermodynamic phase transition. And in fact, it does. In fact, if you compare numerical simulation finite size, they compare very well with the exact analytical solution at equilibrium. And the nice thing that we also found, I think, was the fact that you could study the system both from a thermodynamic point of view and from a dynamic point of view. And in fact, if you study the largest Lyapunov exponent as a function of the energy, you see that it has a peak at the critical point, which corresponds to a peak also on the specific heat and in the fluctuations of kinetic energy. And also nice is the fact that if you change the sign, you could study the antiferromagnetic behavior. And in the antiferromagnetic behavior, you don't see the second order phase transition. But you could study also the dynamic part. And here you see that it seems to have a peak. This is, okay. This is kind of peak. It's not a real peak, but in the antiferromagnetic case, both for the largest Lyapunov exponent and also for the Kolmogorov-Sinai entropy. But here is, of course, much more like a peak. But this I'll show you, it's only a finite size effect. In fact, if you go further, you see, and if you extend the simulation for a great number of spins, you see that for all energies and as a function of n, the larger Lyapunov exponent goes to 0 in the thermodynamic limit, while in the ferromagnetic case, this is the antiferromagnetic case. In the ferromagnetic case, you see that it remains constant. So it's not an artifact, but it's real. I mean, in the thermodynamic limit, at equilibrium, the largest Lyapunov exponents remains constant. And so it's a dynamic signature of the critical state of the second order phase transition. But then we went to study also the out of equilibrium regime, which has a lot of interesting properties. And you see here, for example, that it has a negative specific heat here and long-living quasi-stationary states. And then it arrived a paper by Celia and Tenero. I don't know if Celia is here, but you know, Celia and Constantino, who generalized this model, more or less in the same year that the first paper was published. And this is quite interesting because you see that you could extend and study the behavior of this system as a function of the range of the interaction. And you see that here for alpha, this alpha here, less than the dimension of the lattice, then the behavior reduces to HMF, while for alpha that goes to infinity, then you go towards a nearest neighbor model. So we, by chance, saw this paper in TRL, and we start to be excited about it. And so we started to be in contact with Constantino. Other things that we saw also in other papers with Vito Latora was, well, this is actually later, but this is that we have anomalous diffusion, and also the Lyapunov exponent of this system in the quasi-stationary states is less chaotic than in the equilibrium regime. But this is the start of our collaboration. Vito went to this Stat.Phys conference in Paris and met Constantino for the first time. And then we met all together in Boston, where Vito was staying, and I joined him to participate to a conference organized by Michel Baranger. And Constantino came, so we met there for the first time. I think it was 1999, something like that. And we were also very much interested because you suggested in this paper here that these long-living quasi-stationary states could be explained by your statistics. So we were very much excited, and we started our collaboration. And this was the first meeting that I organized in Catania, and you can recognize some people here. Dieter Gross, Vito is here. Constantino was not there. Oh, oh, yeah, okay. Yes, I was wondering where was Constantino. And it was a very small meeting, but it was just the starting. And in fact, we started to publish some papers. This actually was the first one in which we connected this anomalous regime with statistics. And we were able also to explain this decay of the correlation function in the out of equilibrium regime with the Q exponential, which could be connected to the exponent of the anomalous diffusion. So in some sense, I think that this is the first evidence that Q statistics apply in order to explain the decay towards equilibrium of this system. And then it was not only HMF, we started also to work on the logistic map, and for the first time, I think there were some indication already by other collaborators of Constantino that at the edge of chaos in the logistic map, the correct Q to use was the one which is here, 0.24, 24, yes, etc. But with Michel Baranger, who was the tutor of Vito in Boston, and with Constantino, we were able to show it also for the entropy growth, because it was found before for other kinds of dynamics. And then it started with a series of conferences first in Sardinia. This is the one in 2001. This is a famous picture with Eddie Coyne. Eddie Coyne was there. And then there was a second in 2003. And then Constantino started to come to Catania. This is an occasional one seminar in which the triangle emerged, the Q triangle emerged on the blackboard. And then it was the occasion of the 60th birthday, which we were here. And then we start with this School of Complexity in Erice together. By the way, I will leave earlier because I have to go to Erice on Saturday to celebrate the 60th anniversary with Professor Zicchiti of the foundation of the Ettore Majorana Foundation in Erice. Actually, this was not a real school of complexity because it was hosted by a school in solid state physics by Giorgio Benedict. But after that, Zikiki established this new school in Asia. These were the proceedings were done together. And then there was this other famous dedicated issue on Europhysics News on all the possible applications of statistics, and in which we published with Alessandro this picture, which is I think one of the best evidence that shows that statistics apply not only for the HMF model, but also for the generalized one for the alpha XY model, for different initial conditions and different size, etc. And we also found some kind of glassy behavior that Alessandro, I think, will talk about. Then other meetings, this one in Kyoto, organized by Sumiyoshi Abe, and also in Crete with Giorgio Parisi, and just teaching Sirtaki to Giorgio. Giorgio Parisi. And then the sixth birthday of Alberto, and then again another famous conference in Durham, which was the beginning of a series of papers, very interesting, about the generalized central limit theorem at the edge of chaos. And then another important conference in Trieste, where there was a famous debate on the application of statistics. I think Eddie Cohen was again there. And then I also started to come frequently to Rio. This is 2006. Then there was a conference, a satellite conference in Catania of StatFist 23. We went together to Genoa by car. It was a very nice trip. And then we started also to work on this generalized central limit behavior for the HMF model. And in fact, what we found was that even if you look at this property, there is a nice explanation using statistics of this behavior. But of course, you have to be very careful about the initial conditions, which in this case are very, very important. Then a very nice conference, which I still remember in Iguazu, organized by Renio Mendes, who is here. We visited also the dam. And again, Edice, Conophysics Colloquium. And again, Rio. And here in Wuhan, when Wuhan was not so famous for the pandemic. And Constantino is one of his favorite activities, just trying to buy carpets. And okay, then we were here again for the 7th birthday in this room, I think, yes. And again, in Santa Fe with one of the last times that I met Murray Gell-Mann. And then other conference in Edice in 2015. Then again, Mexico for the 7th birthday of Alberto Robledo. Then in Sao Paulo. And in Vienna for the Complexity Science Hub meetings in 2018 and 2022. And again, Edice, several conferences. This is one where we commemorate, because the same year Murray Gell-Mann died, we commemorate, Constantino actually did it, Murray Gell-Mann. And this is the last one last year. You may recognize many of you. And again, he passed from Catania teaching and visiting the house of Ettore Majorana, which is this one. And this year in Lipari, another small island close to Sicily, together with Emmanuel this time. And so this is our most recent co-authored paper with Antonio and Ugur and Alessandro. And this is the one of the best, I think, plot made by Antonio about, maybe we'll talk about this HMF behavior out of equilibrium, which could be explained by Q statistics. So closing and summarizing, 15 co-authored papers, several international conferences, infinite number of interesting discussions, not only about physics, plenty of wonderful moments. It has been really an honor for me and a privilege to meet you and to work with you, Constantino, and happy birthday for your 80th.
Thank you, Andrea,
Was
for showing us so many.
25 years of photos.
Yes, 25 years of photos, so many photos. Nice photos. Does anybody has some comment or question?
Old stories. No, just I like to recollect all the memories.
Yes, it was very nice, very nice. All this history of our friend. Okay, then we go to coffee. Okay. Is everything all right?
Thank you.
Okay. Daqui a pouco você fecha.
Prova? Ok.
Ok. Parece que está dando um eco aqui, ó. And the next speaker, another Italian friend of Constantino from Sicily, Alessandro Pulchino.
Thank you, Fernando. Thank you to all the organizers. Of course, it's a big, very big pleasure to be here for the. I heard my voice here. Moment that. Prova? Oh, okay. A pleasure to be here for this celebration of Constantino, and together with so many colleagues and friends that are. Of course, every 10 years, we say with Constantino, every 10 years for the birthdays of Constantino, these meetings are the opportunity to meet again people, old friends and old colleagues. So I'm very happy for this. And Andrea, of course, showed many pictures of our work, and I just will give you other fragments of the last 20 years of collaboration with Constantino, and if it works, that works. Let me. No, it works before. Strange. Okay. Okay. So, so I will show you just a very few pictures. These are the first two. In 2002, that was the meeting workshop in which I met Constantino for the first time, together with Ugur and Andrea in Santa Fe, New Mexico. It was a workshop about anomalous distribution, nonlinear dynamics, and non-extensivity. And from that moment started the work timeline that ended with the picture that also Andrea already showed, the picture of the Conophysis colloquium, the last step in 2023 of the last July. Constantino is here, and the special guest was also Emmanuel in that time. And I like to show you just this picture that I use very often for my students, that explain very well the position of Constantino with respect to the Boltzmann-Gibbs statistical mechanics. If you put the degree of disorder in the x-axis and the complexity in the y-axis, you see that the strong chaos limit, so this position, extreme right position, is the domination, of course, of Boltzmann-Gibbs statistical mechanics, but it just rigorously applies only to ideal gas, or maybe the universe considered then as an ideal gas of galaxies. Of course, going to the left, the edge of chaos regime of collective organized systems, physical, biological, social, and economics, of course, is dominated by Tsallis statistical mechanics, and exponential and Gaussians are substituted by the well-known power laws, Q exponential or Q Gaussian. This is just to have an idea of what we made of the regime of the age of chaos that in some way describes this long-standing journey with Constantino. This is my PhD thesis in 2002-2004 under the supervision of Andrea and also in collaboration with Vito Latora, and the topic was just metastability, non-extensivity, and glassy dynamics in a class of long-range Hamiltonian model that in principle was the HMF model that Andrea spoken about before, and these are the papers that we published in that period. But Andrea talked about this, and I just will give you as a first step some hints about the glassy dynamics, because I think that it could be of inspiration to, in some way, to explain what we explained with Q statistics. But I think that there are connections that should be explored, and we just we occupied of this just in that period, but probably we should start again to study about this. And the next after 2006 is other papers. Here there is the paper, the first paper with Constantino, that and also Ernesto Borges, that was also cited by Andrea. And again, these papers was considered by Andrea. So I will just as a second step in this talk, will speak just about something about these two papers that was connected with another one of 2006 and are connected also with our last paper with Constantino and also Ugur and Antonio that was published into the special issue Hamiltonian overdamped complex systems, in which me and Antonio and Ugur are editors, and is still open, the submissions of this a never-ending story, because it's open at 2 years at least. Okay, but so we speak about the phase transition in long-range model of couplet oscillators, not only HMF but also Kuramoto model. And then I will close with a third step that is a paper about noise synchrony and correlation, the edge of chaos, with me, Andrea, and Constantino, of course. Annalisa Greco will speak on Thursday about 2 of our last papers, also with Constantino, about acoustic emissions in buildings and rock deformation and failures, in which we performed the Q statistical analysis, but this is on Thursday. And so I will just will limit to this to repropose some sketch of these three topics. The first one was the glassy dynamics. The HMF model was already introduced by Andrea, so I will not speak about more about this. We have at equilibrium the transition from the condensed phase and homogeneous phase predicted by Boltzmann-Gibbs statistics, and this is the caloric curve and the magnetization curve. But as Andrea told, and you know, an out of equilibrium initial conditions put the system in these constrained the system in these QSS, quasi-stationary states, in which we discovered fingerprints of Q statistics and violations of Boltzmann-Gibbs statistical mechanics. And these quasi-stationary states have been characterized by a lower temperature, so the system stay trapped in this for many time in these quasi-stationary states, depending on the initial conditions. The so-called M1 initial conditions, in which you have all the oscillators in the same position. So you have an explosion of kinetic explosion at the beginning. Showed also interesting. This is time in vertical line, and horizontal are the different initial conditions. Showed correlations in the mu space which disappear when you start from initial conditions more homogeneous. So this m=1 initial conditions was very interesting in showing not only metastable states, but also correlations with Q statistics, and Andrea showed correlations, Q exponential correlations, and other features like anomalous diffusion and aging and so on. The point is that we discovered that starting from this M1 initial condition during the QSS regime, so before to reach the equilibrium, discovered that these oscillators, you can consider also like spins, formed some dynamical formation of clusters. So there is a sort of cluster competitions that is sketched by this picture. These cluster competitions, on one end, drives the system to these non-extensive features, as in Andrea's talk, but also to a sort of dynamical frustration. Frustration is, you know, is a characteristic of usually of glassy systems in which there is a sort of quenched disorder. And in this case, is a sort of dynamical disorder. It's not quenched, but is a dynamical disorder that brings the system to show these clusters. This is three-dimensional mu space and the number of oscillators. And you see that there are Pixar clusters of oscillators in the QSS regime that are distributed with a power law. And so there's a power law of the cluster size distribution, and we suppose that this phenomenon of dynamical frustration could drive the system to a sort of weak ergodicity breaking that is correlated to the reasons for which the Q statistic works. In other words, the fact that the system is trapped in the phase space in some fractal structures, and so there is a sort of ergodicity breaking, so-called weak ergodicity breaking, typical of glassy systems, in particular of spin glass systems. So we tried to propose an order parameter inspired to the glassy systems for the HMF model that is a sort of polarization. We call it the polarization that in some way measure the time behavior of the single spins, and is a sort of average of the modulus of the this time average of each spin. And the point is that in the homogeneous phase of the HMF, you have both the magnetization, that is the standard order parameter of the system, together with this polarization are zero, because this is magnetization, because spins in some way rotate on the circles, and the elementary polarization is zero. So you have both order parameters equal to zero, but in the QSS regime that we proposed to be considered as a sort of spin glass phase, you have m equals zero, still equals zero, like in the homogeneous phase, but this polarization is different from zero, meaning that in some way the oscillators are, the spins are frozen in time in that positions, and so the elementary polarization is different from zero. But if you perform an average over a spatial average of the system, you see that the magnetization is zero. So we proposed that in the QSS regime, that QSS regime behaves like a spin glass phase in glassy systems, and meaning that in some way this ergodicity breaking could be related to a sort of complex energy landscape in the phase space. And just to close with analytic part, we using the replica symmetry theory of adopted in spin glass, we were able to find a self-consistent equation for the polarization. This is the polarization as a function of the temperature, and in the regime of QSS regime, we were able to reproduce with applying the replica symmetric solution the behavior of polarization. These deviations were probably related to the replica symmetry breaking introduced by Parisi many years ago, and probably should be explored, and should be explored, in my opinion, also the possible relationship of this behavior with the Q statistics, because both features are present in this QSS regime. And I found that in 2009, some, not for HMF, but for a physical system, was found, a glassy system, a real physical glassy system, was found a generalized formula for the relaxation of the spin glass connected with the Tsallis statistics, so with a connection between the entropic index with the interaction parameter of the spin glass relaxation. So this could be a suggestion to make something more in that direction that we stopped in that year. So probably time to reconsider these results. The second step was about the connection between HMF model and Kuramoto model, because both the model we will see can derive from the same equation of coupled pendula. The Kuramoto model is very famous and is a model, a general model for synchronization of coupled oscillators. This is apparently the equation of motion in some way of the Kuramoto model. This is dissipative driven system, is apparently quite different from the Hamiltonian mean field system, the HMF, that is an Hamiltonian system, so a conservative one and not driven. But we will see that there is a connection, because let me just remember that in this expression, the time behavior of the phases of the oscillators are coupled, depends on the coupling strength of the oscillator and on the natural frequencies that are a driven term, natural frequencies of the oscillators. This is an important point. It depends, the behavior of the system strongly depends on the distribution of these frequencies that stay the same, remains the same for all the simulation of the system. And this is, you can choose these two wide classes of initial conditions, Gaussian distribution or uniform distribution. We will see that this difference will drive to different behavior. And the order parameter is very similar to the magnetization of the HMF model, because also in that case you have oscillators that move in the unitary circle. And is the order parameter of the Kuramoto model is a sort of magnetization, and you can, like in the HMF model, you can decouple you can produce decoupled equations just using the order parameter, in the sense that here you have equations that are independent one of the other, in the sense that they depend one from each other through the order parameter. And integrating these equations, you can study the system, and you can find that the behavior of the asymptotic value of the order parameter has a sort of phase transition from an homogeneous phase to a partial synchronized phase. It's impossible to synchronize perfectly the system due to because in that case you have 0 here, so you have the paradoxical situation in which if all the angles would be the same, you should have the oscillators rotating at their natural frequencies. That is a sort of paradox. So you can just reach values near 0.8 or something else in the perfectly fully synchronized phase. So this is a phase transition that it's similar to a second order like phase transition, like the HMF1. And the analysis of Kuramoto was able to find the critical coupling analytically, and that says that the values of the critical coupling depends just on the central value of the distribution of the natural frequencies. So they are very important. Okay, I will show you in a moment that if you start from a dampened driven coupled oscillator, system of dampened and driven coupled oscillators, or coupled pendula, if you want. So this is the general equation of the system, in which you have also a part of the coupling term, the order parameter. You have also a damping term, the first order time derivative, and the driving term. If you start from this equation, we showed in 2009 that the conservative limit of this equation is the HMF model that you can obtain, putting, of course, the damping to 0, the driving to 0, and the coupling to 1. And these are the equation of motion, the coupled equation of motion of the HMF model. On the other hand, if you take the overdamped limit of the same equations, you can reach the Kuramoto model equations. And it's interesting to notice that this is the second order phase transition of the HMF model that presents, as Andrea showed, a peak of the largest Lyapunov exponent in correspondence of the transition, and the same happens for the Kuramoto model. This is the second order like dynamical phase transition. This is the peak in the largest Lyapunov exponent for the Gaussian distribution of initial condition. This is for uniform distribution. You can pass from one to another one just by choosing a Gaussian distribution with variable sigma. And for sigma equal 1, you have the case of the Gaussian solution and the Gaussian distribution. And for sigma large, very large, you recover the uniform distribution. Through this trick, we were able to design this phase diagram in which for every value of sigma as a function of the coupling kappa, we recover different regimes. The interesting thing is that in the partially synchronized regime, you have a fully chaotic situation with positive Lyapunov exponent, but on the other hand, in the incoherent phase, you have a sort of edge of chaos situation in which the Lyapunov exponent is close to 0. And the two things to observe here, that in a certain part of the partially synchronized regime, you can recover metastable state in the Kuramoto like in the HMF, similar to those of the HMF for some values of k near the phase transition. You see that the system remains trapped for a quite long time in some metastable states that resembles those of the Kuramoto model of the HMF. But another interesting thing is that in the edge of chaos regime, if you perform the central limit behavior procedure introduced by Ugur and Constantino and Christian Beck in 2007, if you apply this procedure to the Kuramoto model, when you have 0 Lyapunov exponent situation, you can recover Q Gaussian attractors of this sum, rescaled sums. This for both the uniform and the Gaussian initial conditions. But if you put the system in the fully chaotic regime, you recover the standard Gaussian attractor, both for the uniform and the Gaussian initial condition, of course, in presence of positive Lyapunov exponent. Just a sketch of the last step that was in 2013. We passed from continuous systems to maps, and with Constantino and Andrea, we took the Kaneko, analyzed the Kaneko so-called CML model of coupled logistic maps in this case, no more continuous oscillators, but coupled logistic maps, in particular a chain, a lattice, one-dimensional lattice of maps whose states at the iteration t+1 depends on the state of the same system at times t, and also on the state of the first neighbors, depending on the strength of this local coupling. For coupling equal to 0, it depends just on the map. For coupling equal 1, depends just on the neighbors. And if you put the maps in the fully chaotic regime of the logistic maps and vary the value of the coupling, this is the model of Kaneko, you recover different situations. This is time in the vertical line, and the horizontal line is the chain of maps. You can recover some patterns of synchronization emerging together with spatiotemporal chaos, so what we call fully developed turbulence, when of course the coupling value of the coupling increases. This is maximum value of the coupling. In 2005, Li and Fang proposed to introduce a long-range correlation to induce an on-off intermittency in the system. So you have a linear chain with the long-range correlation induced by the rewiring, like in a small world network, and you can recover this intermittency. We proposed to obtain the same effect, not rewiring the chain, but just putting in a noisy environment. So we add an additive noise to the system, to the equation of the system, that is a random variable extracted in the interval 0 sigma max. So sigma max is maximum level of noise, and we tried to put in relationship the maps just because they stay in the same noise environment. But another difference with Kaneko is that we put the logistic map at the edge of chaos, so at the critical point, no more on the other point, and we recover correlations, as you see, just for a low level of noise. For low level of noise, you have an intermittent situation, but when the noise increases, we have just a Gaussian behavior. This can recovered by just plotting the PDF, the probability density function of the returns of the quantities. You see that increasing the noise, you passes from Q Gaussian behavior to Gaussian 1, and this is the behavior of Q that above a level of noise goes to 1. This is in the case of chaotic map. I have just to finish. This is a connection with the analysis of interoccurrence times in finance. I can skip this, and I just arrive at the conclusion. The conclusion is that there was also along this line other steps of more pleasant work. For example, in Mexico, with Constantino verified the chaotic trajectory, the stability of chaotic trajectories in the non-Sinai billiard, the standard billiard. But also, I spoken about acoustic emission. We study also the effect of acoustic emissions on the walls of the Ettore Majorana Center in Erice, in which there is a very nice piano that I want to finish by. No, of course, doesn't work. Happy birthday, Constantino.
Thank you, Alessandro, for the
We saw
very
that
nice
there
talk.
is a piano here, so maybe we
Yes,
we can repeat for the audience maybe later. Thank you.
And thank you for the piano concert. Questions?
Evaldo.
Short question. We have been working on Ginzburg-Landau equation for 1D and 2D, and one dimension, 2 dimension, Ginzburg-Landau equation. And in 1D, we are also using, instead of additive noise, multiplicative noise. Concerning the CML, the couple mappalets, what do you expect if you use a multiplicative one instead of the additive noise?
So if you put multiplicative,
yes,
what do you find? What do you find?
A different Q, for example.
The question is the question. Okay. No, we didn't try to put the multiplicative noise, but it could be an interesting thing, because just with additive noise, we recovered the whole possible behavior. So we didn't have the necessity to put a multiplicative noise, but it could be, I don't know, but it could be a good idea. So we will, thank you. We will try in the future.
There is the last question by Evaldo.
Thank you, Plutino. For the spin glass phase you obtaining the HMF, you have two scenarios for spin glass, a droplet one and a mean field one. As you have here a mean field model, which scenario is there in your case? I believe maybe is Paris scenario, no?
The droplet was that of Bouchot? No. Bremont, yes. No, we didn't analyze this different, but I think, as I said before, that because actually we stopped our work about this at that time in 2004 after my PhD thesis. We published several papers, but we passed to others. But I think that probably this your suggestion could be a starting point to analyze better this system, maybe with of course the tools that today are available after 20 years. So probably, and to find more connections following that paper that showed maybe some suggestion to bring to make a connection, more stringent connections with the entropic index and between the entropic index and the polarization that I think that describe very similar situations in the phase space. But of course, we will do in the future. Thank you, Evaldo.
Okay, let's thank Alessandro.
Thank you.
Next speakers, Renio Mendes. He's very famous for his jokes, but he said he's not going to tell jokes today.
Sì. Passi il microfono.
That's okay. The pointer, please. How to work. Muda. Volta. Esse é para apontar, esse para mudar, esse é para voltar. Good morning. Today is a pleasure to me see you and especially Constantino Tsallis here. This work is in collaboration with these three guys. Constantino, please look at the face. A happy day. Okay. Let's continue. Would you like to say some words about my timeline related to Professor Constantino? In the last millennium, the end of the last millennium, Constantino went to Maringá, give some seminar. That opportunity, I know Professor Constantino. So that opportunity, I am something like without direction in my scientific work. So Constantino Tsallis asked me, think about visit CBPF and to work with me for some time as a postdoc. So I arrived here in 1996. In that opportunity, I know many of you, in particular, where is Luciano? I arrived here and found Luciano in Portuguese, este gaiato. So, Constantino visited Maringá in some opportunities. In that time, start our graduate course in physics. So Constantino was in the master committee, the second master committee of our graduates, and the first PhD committee. After this, I talked a lot with Constantino and other members of ENCT. Okay, this is a long story. I continue. But when discussing with Constantino, in some cases, he disagreed with me. Of course, suppose you are a big family. So in some moments, we disagree one from someone. It's like when you have a girlfriend, she asks, let's discuss about the relationship. Understand? In all opportunities, there are divergences. I will talk about divergence with you. The most famous divergence is in the Kullback label 1. Initially, you have the usual entropy, and you replace this entropy putting a reference PDF. So this divergent or relative entropy give us this inequality. If you have the PDF equals to the reference 1, this is 0. In contrast, this is greater than 0. Okay? This is the main property of this entropy. Some years later, Tsallis proposed other entropy, Tsallis 1, and this is a way to write this entropy, Tsallis entropy. And later, 1998, he proposed other divergent, Tsallis divergent, replacing this usual logarithm, but Q logarithm give here. Okay. Some years later, Nautilus proposed a generalization of logarithms, a broad generalization of logarithms. In this case, if you have this function g, this function must be positive and its derivative must be positive too. You can choose a multiplicative constant. This constant is in general chosen in such a way this reduces the usual logarithm when you use g equals to y. The Q logarithm is recovered when you use a power law. Okay. So the usual entropy can be changed, incorporating this generalized logarithm. In such a way, you can put a new divergence based on this generalized logarithm, very similar to the usual one. It's curious that kind of generalized logarithm obeys a similar inequality as usual logarithm. Because of this property, this d is greater or equal to zero. Okay? For positive x is here the demonstration. Okay. But 1961, 2 years before I appeared in this world, Reni proposed a generalized divergence. F, you know, is as F divergent. If you compare F divergent with this one, you can identify this F with minus generalized logarithm. In this sense, recover this structure. Okay. In the same work, Reni proposed an entropy, another entropy, Reni entropy. This is one. In the same work, Reni introduced a possibility of a divergence. Use a reference PDF to compare the other PDF. Of course, if you take the limit of any entropy, alpha goes to 1, recover the usual entropy channel 1. Oh, sorry. Yeah, no, sorry. And when you take the limit of alpha goes to 1, this divergent, any divergent, recovers the Kullback label 1. Okay, let's continue. Now you can replace in any entropy. You can replace the usual logarithm by this generalized one. You have a new class of entropies. But you can found the Reni divergence, the generalized Reni divergence in this way. So a new class of divergence. Okay, you can choose a particular case of generalized logarithm. Many days ago, where is Ananias? Ananias isn't here now. Ananias used for Tsallis entropy the name Tsallis entropy. After this, all of them use this name Tsallis entropy. Now, because it's a birthday, I give a name for something. If you put this, replace this logarithm by the Q logarithm, you obtain a new entropy and a new divergence. So a kind of a gift for this birthday. I use the name Reni Tsallis entropy for this one, and for this divergence, I use the name Reni Tsallis divergence. This, of course, isn't a good gift, but it's the only one I have in this moment. Okay, let's look for other way to think about divergence. As a motivation, we start from Kullback label divergence again. This is the Kullback label. The reference PDF or zero can be written in terms of a potential. You can always choose a potential in such a way, obtain this reference PDF. If you put this reference PDF in this equation here in the definition of Kullback label, you obtain the right-hand side of this. Look, this is a difference from the free energy and the free energy related to stationary state of the system. Look here. This is the mean value of the energy, and this is the entropy minus entropy. And if you put here the reference probability, this one, here and here, you obtain the usual free energy. But beta, V is a fictitious one potential. and beta is a fictitious temperature. You can choose anyway the beta value. In particular, you can choose beta equals to 1. So this reduces to the free energy minus the free energy, equilibrium free energy. Okay? Of course, you can put this related, it's well known, there is a lot of research about, for instance, Fernando D, Evaldo, studied a lot of things related to a theorem. In particular, the most famous case, the usual Fokker-Planck equation, if you use the free energy, this one, you can take the time derivative of this functional free energy and obtain this inequality, indicating that when the time goes to the infinite, F goes to its minimum value, okay? And A is the force, and it's related to the potential, this derivative. Okay. Now I generalize a theorem to consider a broad situation. In contrast that the situations where Fernando Nobre and Evaldo investigate, in the case, they start from a diffusion equation or Fokker-Planck equation and try to obtain the free energy. Here, you consider other situation, imagining a free energy. So if you consider a free energy, you take in this equation the functional derivative of this free energy, and this becomes a diffusion or Fokker-Planck equation, generalized. So the orders is different. One case start from the equation and obtain the free energy. In this case, start from the free energy and obtain the equation, okay? For instance, in this equation, this is a non-negative function, in general arbitrary. In particular, if you take this case and this case, we recover the usual Fokker-Planck equation. Okay? Here, I am following the Frank procedure to investigate a theorem. Okay, how to demonstrate this theorem in one page? It's very easy. Consider the time derivative of the functional, and in this case appears this derivative in time here. So we use this right-hand side of the equation to obtain this part. After this, proceed to a integration by parts to obtain this line. In the following step, what you need to do? You need to consider the PDF goes to 0 at infinite. In this case, this is term goes to 0 because the fundamental theorem of calculus. So remains only this time. But this function is non-negative. It is part, of course, is non-negative. You arrive to the Egg theorem. How to construct from this a divergence? Very simple. For a long time, F goes to its minimum. But the divergence must be bigger or equal to 0. So we take this free energy and subtract the equilibrium one. In this case, this difference is 0 when the reference probability is when this probability goes to the reference probability. So this gives 0. So this is positive and equals to 0 when we are in the equilibrium. In the case of Tsallis context, you need to choose a free energy. We use Tsallis entropy and mean value of the potential. If you use this F, you obtain this equation, Porozzo-Midge equation. We remark here the first time this connection between Tsallis statistics and this nonlinear equation was given by Plastinus. Okay. So in Tsallis context, the reference probability is just a stationary solution of the equation. This is given here, introducing the potential V. This exponential is the inverse of the Q logarithm, the Q exponential. So when you put this PDF in the previous, when you put this PDF here, you obtain, replacing this V, you obtain this expression. Okay? After this, you consider the free energy with the reference probability and use this relation. After this, you obtain this new type of divergence. This divergence, this divergence is different from that one proposed by Constantino. This divergence was considered particular case related to Tsallis statistics by Nauditz and Semioshi Abe, isn't it here? Yeah. Okay, so gives different way to found divergence. I am ending my presentation, but before I need to say something to Constantino. As explained before, I have two things I need to say. One, I won't remain here on one day. Tomorrow I will go to Maringá because Maringá is a week of physics, like and I meet you in the past. So I am I don't know in English. I am the oldest teacher of this department, so I need to be present there. I give a joke in Portuguese, sorry. Me disseram que eu sou o decano e não decano. Entendeu? Constantino precisa um pouco mais em português. Ontem, entendeu? E teve um jogo da Libertadores ontem. E quem fez o primeiro gol do Fluminense foi Decano. Perfeito. Então, sorry. Return to the English. Return to the English. So, Constantino, as I said in the beginning, I was without a not clear direction in my scientific career, and you help me a lot. You don't know how you help me, but I know. So thank you a lot. Oh, I'm so sorry. I would like to give the conclusions. My fingers are in divergence with me. So we discussed two distinct ways to generalize divergence. And we verified that it's possible use a theorem and in connection with Fokker-Planck equations to unify these possibilities of divergence. Is this? Thank you again.
Okay. Questions?
I would like to say that when I met Renio, I gave a seminar in Maringá, like 9 in the evening. And the next morning, at 8 in the morning, I was again at the university, and he was calculating on the blackboard the equation of states of an ideal gas for an arbitrary value of Q. So he listened to my talk 12 hours earlier, and he was already calculating the equation of states. So, and I arrived and I saw the blackboard, and I saw that the equations were correct. And I thought, my God, this guy in 12 hours, he heard for the first time a new theory, and he's already calculating the equation of states. And this is why I invited him to come to CBPF. And it was a big success.
Okay. Any more comment or question? Then we end up with this section. We come back. 2:30, okay? For those that do not know, 5 minutes from here, we have a big shopping with all kinds of restaurants, fast foods and everything,
Thanks.
including McDonald's.
Thanks for no divergence.
introduction, actually it is related to the most recent work that we did that addresses some points of the keyword. But I will leave this topic for the end of my presentation, and I will ask your permission to start revisiting the long-term collaboration of Constantino with our group at Universidade Federal de Alagoas. So the first visit of Constantino that I could trace to FAO was on 1976, almost 50 years ago, almost 50 years ago. But it was actually during the 80s that Constantino supported an emerging research group in statistical mechanics at FAO, and he had some scientific collaborations with several colleagues, among them professors Evaldo Sarmento, Roberto Jorge, Solange Bessa, who is here with us, and Uriel Costa. And Roberto Jorge was my undergraduation advisor at that time, and in 1984, during one of Constantino's visits to Maceió, Roberto introduced me to Constantino and asked me to show to Constantino the project that I was doing at that time, and I was very proud to do that. I will return to this presentation in a few minutes. And it was later on in 1997, during another visit of Constantino to FAO, that we started to develop the work relating the Q parameter of statistics with some scaling exponents of multifractal attractors. This is the most famous paper that we did in collaboration. So in the total, Constantino has 27 articles that were published in collaboration with colleagues from UFAO. It's a finite measure of your total. So let me revise some of these works. Let me revise those. The first paper that Constantino published in collaboration with a colleague from UFAO was this one in 1982, with Evaldo Sarmento and Yvonne Fittipaldi. In this work, they were interested in studying phase diagrams of disordered ferromagnetic systems using so-called at that time an effective mean field approximation. Yvonne Fittipaldi was the expert on that approximation. Unfortunately, Fittipaldi was one of the victims of COVID, but I'm sure that he would be very happy to be here today and would have very funny histories to share of us. The second work I would like to bring to you is this one published in collaboration with Roberto Jorge in 1983, also studying random ferromagnetic systems, but now using a kind of real space randomization group approximation that had been introduced by Constantino at that time. And they showed that this approximation could capture very well the exact results in this Q POTS model. And Roberto Jorge also is not with us. He was victim in 2019 of some heart problems and left off. It was in that period that Roberto Jorge asked me to show Constantino my project. In 1984, I was just a 20 years old student, very proud to show a research project to a very famous scientist. So the problem that I was studying was so the project was a study of a spin ladder, a frustrated spin ladder. So I showed it to Constantino how I had computed the partition function, how using the partition function, I computed the specific heat curves, frustration diagrams, what was the trends of the specific heat curves. I was very proud to show him everything that I knew at that time to Constantino. And Constantino made just one simple question for me that I bring it till now. He just asked me, why? Why this curve has 2 peaks? He was not interested in how I computed it. Why nature behaves like that? So that, as scientists, I learned that we should be more interested in knowing why nature behaves like that than just to describe the behavior of nature. Constantino was also the PhD advisor of Uriel Costa. This was the first paper they published related to his PhD thesis. Also, a renormalization group study of Heisenberg models with a free surface. And I have to say, Uriel lost a long fight against cancer in 2019. 2019 was not a very good year for us in Alagoas. We lost Roberto Jorge and we lost Uriel. He's another guy that would have very funny histories to share. Constantino also had a publication with Solange, also studying ferromagnetic systems with an interface using renormalization group, real space renormalization group approaches. This is Solange. Solange 23 years ago. And this is Solange now, a very happy lady. Here he was paying attention to something. He's just having fun. Okay, in 1997, during the visit of Constantino to FAO, we started to study the problem of the sensitivity to initial conditions at the critical point of some nonlinear maps. And we showed that the sensitivity to initial conditions at the critical chaotic point behaved like a power law, and we could relate this exponent of the power law with the Q parameter of entropies that evolves linearly in time. And we showed in this first paper, in collaboration with Uriel and with Plastino, how the Q parameter depended on the degree of nonlinearity of the underlying map. And it was just a couple of months later that we realized that this Q parameter was directly related to a couple of critical exponents characterizing the multifractal attractor of the map. So this was very well received by the community, and we had lots of examples using the logistic map and the SQL map that this relation is exact, although it was derived using general scaling arguments. So after this paper, Constantino motivated me, asked me to organize a meeting at Maceió. So we organized in 2000 this conference, the fractal aspects of complex systems. I know that many of you were there at that time, and I was very happy to find this photo. In the same frame, we have Professor Stauffer, Professor Uriel, and Professor Paulo Murilo. Professor Paulo Murilo. No? I'm very glad to know that tomorrow we have a special section dedicated to Murilinho. My personal collection. So, Tadeu is there, and Aldo is here. Professor Liaci is here. Liaci, Professor Heber da Cruz, Professor Grebode, Luciano, Stauffer. Okay. At that time, Constantino put me in contact with Ugur, and we started to study this sensitivity to initial conditions problem in several complex systems. I visited Ugo in Turkey in 2002 during the World Cup. So the semi-final Brazil and Turkey, I was watching together with him and a few Turkey colleagues. Yes. And in the 60th birthday of Constantino, I participated of the meeting celebrating his birthday, showing this work that I had done in collaboration with Ugo, studying the sensitivity to initial conditions in the backsnapper model. Regretfully, I was not able to attend the 70th birthday. I was in a period in Paris, so I could not come. But here I am for the 80s. And the title of my presentation is related to this paper that we published in 2020. It was done in collaboration with a colleague from Pernambuco, Universidade Federal Rural de Pernambuco, Adalto de Souza, with Professor Carlos Argolo from the Institute, the Federal Institute of Science and Technology of the state of Alagoas, Professor Irã Glera from my institution, and Fabiana dos Anjos, who was a PhD student at our program. So the problem that we addressed was the Levy branching and annihilating process, and we studied some dynamic scaling laws. We looked at the emergence of extreme values statistics, and also the emergence of generalized Fermi-Dirac distributions in this problem. Let me give you just a hint what we did. So the model that we studied was the pure Levy branching and annihilating process along a line. So the process is actually splitting in two. The first process, we have a branching. So each particle branches generating a given number of offsprings, as the dynamics does not depend on the number of offsprings that are generated. Our simulations were done for just n equals to 1. So each particle generates one offspring. And this offspring is placed at a distance r from the original position, with this distance coming from a power law distribution. So the exponent alpha actually governs the range of this branching process. And besides the branching process, we consider the annihilation. So when a particle, when an offspring is, when we try to place an offspring at a site that's already occupied, both particles are annihilated. So we were interested initially in trying to see how this long-range character of the branching processes affects the dynamics of the growing process of the number of particles. So here's a plot, space-time growth of the space-time growth process. So we start with just a single seed at t equals 0, and the seed starts to branch, and when they branch to an occupied site, we have annihilation. So within the growing cluster, we have some voids due to the annihilation process, but this growing cluster evolves in time with not much rough interface when the branching process is short-ranged. When the branching process is long-ranged, the interface becomes much rougher. And notice the difference in the scales here. So the scale here comes from minus 4,000 to 4,000. Here is one decade longer. But the interface becomes much rougher when the branching process is long-ranged. So what we did initially was to understand how the range of the branching process affects the dynamics, because we knew that the average number of particles and these fluctuations, the average of the square displacement, square deviation, we knew that for short range processes, these two parameters, the average number of particles and the fluctuations, both grow linearly, both grow linearly in time. Oops, sorry. So what we saw was that indeed, as the branching process becomes longer ranged, the growth process becomes faster. However, the change from the linear behavior is different, has different thresholds for the average number of particles and for the fluctuations. The average number of particles starts to grow faster than linearly just for alpha smaller than 3, but the fluctuations start to deviate from the linear behavior for alpha already smaller than 4. So we have an intermediate regime here, where the average number of particles evolves in time as in a short range process, but the fluctuations are anomalous. And for when alpha approaches 2, these two quantities show an explosive growth. We develop an exponential explosion because the annihilation process becomes irrelevant when the process of branching is to a longer region that is still empty. So this was the first step of the study. There was a second step that I'm not going to show you. It was related to the emergence of extreme value distributions. The average number of particles fluctuates from one realization to the other. And these fluctuations, when the process is long ranged, is dominated by the longer particle that is generated in the branching. So these external values dominate the statistics, and we have the emergence of a fresh air and Weibull and distributions. I'm not going to show this to you. I'm going to show the part that was related to the keyword. So we measured the average, the distribution of the occupation profile, the average number of particles at a position X. Let me return here. Oops, sorry. I'm going. So we just measured as a function of the position, the average number of particles for different realizations. So at the center of the growing cluster, the average number of particles is a constant. It's 1/2, because sometimes there is a particle, sometimes there is not a particle. So in average, it's 1/2. And this density of particles decay as we cross the interface of the growing cluster. So what we found was that this profile has a Fermi function form with a Q exponential when the process is long ranged. So for large values of alpha, for example, for alpha equals to 4, when we knew that the average number of particles and the fluctuations are normal, the numerical data fits exactly with the usual Fermi-Dirac function. But when we have a long-range process, the decay of the density of particles as we cross the interface is much slower, is power law. And here in the inset, we have the fit for the case of alpha equals to 2.3 with a Q Fermi-Dirac function. For alpha equals to 2.3, this Q parameter was around 1.5. There were another things to explore in this problem that we did not, but I noticed, for example, that when the process is short-ranged, this beta, this effective temperature parameter, evolves in time, and actually the temperature decreases as time grows, as time evolves. But when we have a long-range process and the fluctuations are anomalous, this temperature parameter is time-independent. But it's not much explored in this problem. So this was the last connection that we did with the keyword in this work in 2020. This form for the the Fermi function actually comes from an approximation that's called the factorization approximation, did by one of our colleagues in one paper. I don't know. Probably the author is here, but I'm not remember the name now. Okay, so this was the work that I would like to show you for this event. And in just one more slide, I would like to give a spoil of what I intended to present in 10 years from now. I'm studying together with some colleagues from Universidade Federal Rural de Pernambuco, data from an experiment of collective swimming of zebrafishes. Zebrafishes are a very popular and animal model in biosciences. Yeah, bioscience. So we get some zebrafish, we put in a tank, and we monitor the movement of each one of these fishes as a function of time. So we recorded it, or they at the Pernambuco recorded the trajectories for 5 minutes using 5 different samples with this different number of fishes in each experiment. So the number of fishes in the aquarium ranged from 2 to 30. We have more or less 12 different numbers of fish. For each number of fish, they performed the 5 samples, 5 different samples. And unfortunately, the guy from the biosciences department said that the protocol was that after the experiment, the fishes were so stressed that they have to be discarded. So lots of fishes gave their lives for this experiment. So one of the results that we are finding is that, for example, when we measure the average polarization of the fishes, this average polarization fluctuates in time, and the changes in the polarization has a distribution that is Gaussian, but it is Gaussian just for large values of n. So when the number of fishes within the tank is large, they started to swim uncorrelatedly, and we develop Gaussian, normal Gaussian fluctuations. But when we have a small number of fishes within the aquarium, they start to move, to swim in a very correlated way, and the fluctuations, the distribution of the changes in polarization comes out to be a Q Gaussian. And for 2 fishes, the exponent of the Q distribution is 2. So we have the Q value changing from 1 for normal Gaussian behavior up to 2. There are other quantities that we are analyzing, but it seems that this Q Gaussian distribution actually appears when the number of fishes is smaller than a given threshold. And we are relating the size of this critical cluster with the ability of the fishes to swim in clusters. So it seems that the clusters are formed with 3 or 4 fishes. 1 fish going ahead and the lateral ones following the leader. So we have clusters of 3 and 4 fishes, and these clusters move somehow in a weakly correlated form. We have strong correlated clusters and weak correlations, weak interactions between the clusters.
Have you calculated a normal even exponent?
No. We just we calculated, for example, how the average polarization depends on the size of the number of fishes within the aquarium. How the average polarization decays, because the average polarization decays as we put more fishes, because they start to swim uncorrelatedly. And we have 2 regimes. We have one regime for small values of n, 1 power law, and a second regime for large values of n. 2 exponents. One is twice the other. one slice the other. And we think that we can explain this with the heads. So it will appear in the, briefly. Briefly, these papers are going to appear. Uh-huh. Yeah, I know. The anomalous diffusion, you say how the average region that the fish swims scales with time. Yeah, it's very difficult to say. Yeah, yeah. But that's you see, this is not easy to measure, because if you take this as t equals 0, you pick one of the fishes and see how it moves, but it not moves diffusing. It flies along the way, and it flies, and he tries to swim around near the border. So to see a scaling law as a function of time will not be easy, because we have this finite size, the effect of the tank. So we are measuring scaling exponents related to this number of fishes within the aquarium, and we are seeing two different swimming regimes: a regime where the fish swim strongly correlated, and a regime that they swim weakly correlated. It's the diameter is 40 centimeters. 40. The radius is 20. The radius is 20. And we put that at mostly 30. But we noticed that above 13, we have one regime, and below 13, we have another regime. Yeah, we have it, but we are. Nah, sure, please tell me. And this is not our argument. Our argument is, I will discuss during the questions, because the chairman is asking me to stop. So just to finish some final remarks, I would like to thank Constantino again for supporting our group at Federal University of Alagoas. So we are all here celebrating the influence that you had in our lives, and I'm sure that we will all have a wonderful week here together, celebrating with you your birthday. And as a final message, so as in keyword, the relaxation towards equilibrium is very slow. I wish you much longer life and much more years to come and new histories to live. Thank you very much. Congratulations.
Thank you, Marcelo, for the nice talk, some memories, and very interesting things. Two questions.
Yes.
Okay.
Muita coisa para mostrar.
Okay, thank you, Marcelo. You increased the number of fish, but keeping the same size of the aquarium.
The same aquarium.
So should be a relation between the number of fish and the size of the aquarium, such a way that we have something related to swimming paths of the fishes, no? What do you think about?
Well, if the way that we are reasoning to understand these two regimes that are appearing seems to not depend on the size of the aquarium, but to confirm this, we would need to make another experiment with a different aquarium. It's not easy to do, because when you do a larger aquarium, it's very difficult to make a uniform illumination, and this interferes in the swimming process. And when we put a smaller aquarium, we had to put a smaller number of fish, so 30 fishes is too crowded. But our reasoning, I can discuss with you later. Our reasoning is that this number 13, 12, between 10 and 13 is a number related to the capability of the zebrafish to form small groups. If they bunch together, the size of the aquarium will not be relevant. They bunch together, so the size of the aquarium will not be relevant.
My question is somehow related. Is the depth of the tank?
It's a shallow tank.
So we can consider
avoid the three-dimensional.
Okay, that was it. Okay.
Shallow tank.
Okay.
Other questions?
Just trying to complement the question of Evaldo. You know, there is this transition from what they call Knudsen diffusion, when you have a very diluted gas, and of course the mean, the length of the mean square length doesn't depend on the recipient.
Yeah.
So maybe you have a transition from Knudsen to Gaussian diffusion, normal.
When the number of fishes is larger, we have some like a Gaussian process. But when the number of fishes is smaller, they are strongly correlated, and it is this strong correlation between the swimming of the fish that induces this new behavior. No, it's interaction between the fish. They start to move together, and this reduces the fluctuations in the polarization.
Marcelo, thank you for the talk. And it's just a comment. It's not exactly a question. Are you familiar with the work of Jan Kauzin?
No.
Okay. He's a biologist. He has wonderful, lots of money. So his tanks are really, really big. And he does some interesting experiments where he uses some way of doing some artificial imaging of a neighboring fish that is changing all the time with the guys. And yes, the fish follows the image. So it's really something maybe like a Knudsen thing, that it doesn't matter what is the size of the tank. But really, you should read, because he has lots and lots of experiments, and very nice experiments with the zebrafish. Thank you. I send you the correct thing.
Thank you, Marcelo. And I'm sure that you will have the talk before the 90th birthday of Tsallis. Okay, the last one.
So as far as I know, collective behavior is because of all these coupling functions. And then in general, like if you check these ants, for instance, they do basically release some hormones, and then they do start interacting. If there is like enough number of ants, they can interact between each other, and then they start doing this. So collective behavior is all about couplings and then how they interact. And then as far as I know, fish schools, they do this kind of communities with respect to their visions. And then if they have, somehow 6 degrees of separation is the information approaching from a part of the community to the other part. So if they're all connected somehow, then they have the coupling network there is, then which means they can do the collective behavior. And then as far as I know, Ein Cousin, so he's working on this for a very long time, and you might check this out. Okay. So we can later.
Thank you very much, Marcelo. Help us thank. So the next talker is Ugu.
Tá ligado? Agora sim. Okay, so now it's even better. Our aim will be to explore the connection between scale-free networks and Q statistics. And in order to do this, we need to have a method. So the method is to propose a growth model to do this. So, whoops. Now it's okay. So how are we going to do this? Well, we are going to construct a single connected network of sites and links by gradually making it to grow. And what are we going to do to first fix one site, call it site first site, at some arbitrary origin of the plane. Therefore, the space is two-dimensional. Then how are you going to take the second site? Well, you are going to choose it randomly and isotropically at a distance r distributed according to some probability law, and we are going to use this growth probability, right? Then this second site, of course, will be linked to the first one that you have, and then what are you going to do next? You locate the new origin as the barycenter of the two existing sites and apply again the same distribution from this new origin and locate the third site. And then this third site, of course, will be linked to only one of the pre-existing ones. And how are you going to do this? Well, you are going to need another probability. We call it attachment probability. And we use this kind of probability. I call it attachment probability. And here R is the distance of the newly arrived site to the ith site of the pre-existing cluster. And this K is just the connectivity, which is defined as the number of links already arriving to that site. And by definition, of course, you immediately understand that K1 and K2 is just one. And then you are going to repeat this process. So, for example, you can do it n times, and then you have this probability over there. So you see immediately from here, the dynamics of the model makes the arriving sites to have some preferential attachment to the previous sites that have many links. We call them hub. Of course, as long as they are not too far, because there is also this guy here, right? So, so whenever you look at it, this competition between the connectivity and the Euclidean proximity would be less pronounced whenever this attachment parameter is close to 0 and disappears only with this condition. And if this happens, then you are on the regime of Barabasa-Albert. So this is kind of picture like this, if you like, in 2D, as you see. And what happens is that when you look at the connectivity distribution, this growth parameter controls the metric, of course, but has no influence on the connectivity distribution. You see several values gives the same result. But on the other hand, for the other parameter, which is attachment parameter, it has a big influence on the connectivity distribution, as you see here. And they just use Q exponentials to fit these results. And it seems it's working, as you see here for various values of Q. And you can see such a Q versus parameter graph having your Q values. But the story does not end here, because then they look at the role of the dimension. Then what you are going to do basically is that here you have 2, and if you generalize it to D dimensions, you can look at all possible dimensions of the space where your network is put, right? So therefore, you can have 1D, 2D, 3D space, and you are going to use the same attachment probability. And you see immediately over there is again, for all dimensions, your distribution is independent of a growth parameter, whereas it is dependent on the attachment parameter like this. Here you see each color would indicate different dimensions. Okay, so this is kind of easy to see, and you see a nice data collapse here given by this function here. You see many parameter values together with different dimensions from D1 to D4, and it's over there. And Barabasi Albert is just a point here over there. Okay, so this is something about connectivity distribution. Now, the third part basically is about exploring energy distributions. So, so now you see a hub here, and this hub or each link has some width given by this omega, and you can define an energy of any site, and just by defining it, half of the sum over all link widths connected to this site. Okay, so this is called energy in this case. So we have therefore this growth probability. So you are going to, of course, choose a random number from some distribution, which gives you the linked weight, and energy of site will depend on how many links it has and the width of those links. So you are going to use a probability for this, and this is the probability to have this. And for this probability, for example, you can use stretch exponential distribution given like this, and you see here an example where this exponent here, eta is 1, and this omega 0 is 1, but you can use other values for that. This is just one case that you can see it immediately. And Q exponentials are also there whenever you look at the energy distributions. As you see, you can again fit them. This must be energy, you see. Okay, so, but you see the system. And now I'm going to look at these two cases. Here you see one example. Whenever the attachment exponent is 2 together with D, then it is 1. This number is 1, then you are here. Then it is 4 divided by 3, it is 1.333. And the other one is here. From this, you can just find another value of Q, and you can check it, of course. It's okay. But then comes the fourth episode, exploring the finite size effects. Starts with this paper, but we are now having better results. What we are doing basically is that we conjecture finite size effect can satisfactorily be described by this equation, this differential equation. And if you look at this differential equation, you can immediately recognize that there was a solution like this, and this integral can be solved numerically. This is what we are doing, and you see the results here, starting from a small value of n up to a large value of n like this, and just with the parameters mu r and r, you can just fit this better and better if you go large and limit over there. and the finite size effect is just here. And it seems that our conjecture is doing very well. Like this, you see here two examples just to see. One is here, the larger n case is here, and if you can make it larger, you will be at this point, then this point, and you go, it seems you go forever. Why I say so? Because as n grows, the tendency to the exact Q exponential is more evident from here, because this mu r, as you see, as n goes to infinity, then you are going here, and it goes to 0 as it should be. Therefore, from our final results, we can think that we have Q exponentials as you go to n goes to infinity limit. Very good. So, very good. I have 5. Okay, very good. So the last episode is this. We are going to explore crossover phenomenon. Well, remember the conjecture. If you have a finite size effect, well, you have finite size effect, of course. So in order to account for finite size effect, we are concentrating on this. We have this integral to solve, and numerical solving this, we have those. Now, what I'm doing, exactly the same, but now I'm not going to use this probability that I was using. Now I'm using this one. This one. So what is interesting in this one, you have this guy here, and as that C parameter goes to 0, you end up with the previous case. But if this C is too large compared to this guy over here, of course, this dominates. So the probability dominated by this, and we know that this corresponds 1 Q exponential depending on this value. Now you have another Q exponential now depending on this parameter here, this exponent, gamma A, another exponent, right? So there will be a, therefore there will be a kind of interplay between one Q exponential to the other. So therefore, our new conjecture is that crossover phenomenon together with the finite size effect can be satisfactorily described by this equation. Now you see here one Q and another Q here, right? This Q prime, I call it. So also there's a beta with the new Q. There's another beta for the first Q. And now your integral is a bit a monster, but you can still solve it numerically. If you do this, then you see I just take one case with alpha parameter 2, gamma parameter 3. So this is to say, if you have alpha parameter 2, and we are using d equals 2, therefore it corresponds to q equals 1.33 case. On the other hand, when you take this as 3, then 3 divided by d, 2 is just 1.5, then you are in the regime of q equals 1.2. So you have two q exponentials to come up, and there must be a crossover. So here you see, just solving the integrals numerically, you see one which gives you this one, 1.2, and the other one with 1.33. It goes in the first line like this, then it ends up with this, right? So this is basically whenever mu r is just 0. So this is another example where you can see this choice of betas makes the position of the crossover different, right? Here you have the crossover like this here, approximately, right? But here, a little bit afterwards, right? So you can also change the position of the crossover, just adjusting beta values. So what we have, unfortunately, for our larger possible n value, we can go up to here. So crossover is somewhere here, so we cannot see it well. Why? Because n, this much n is not allow us to go to the finite size effects appearing before the crossover. But in order to see it, you need to go extremely large values of n. But I would say more to come about this. And this scientific, this physics part, I would like to finalize with this announcement. Most of you know that there is a special issue in Entropy Journal for this occasion of the 80th birthday of Constantino. So you can check it from here, and you can submit your work, etc. Most of the so I'm one of the guest editors, and there are several people here as a guest editor, and I strongly recommend you to send your work here. So here you have some other information, but you can just go to the web page of Entropy and find all necessary information. Okay, so this is the first part of my talk, and I am about to go to the second part. So maybe 10 minutes. Okay, so if there are some questions about physics part, maybe. Huh? Say it. Mm. Two. Conference.
No, yeah. Instead of indicating that link, you should go to next slide and show QR code. Yes, so now
here. I'm an old guy. Come on. Yeah. Come on. Okay. Okay, nothing. Right? So I go to the next part. Basically, our story begins in 1997 when Constantino visited us in Izmir during my PhD. I hopelessly tried to find some photo with this, but since it's too much archaic, I cannot find any, but I found this one. So just think that this is 97, because whenever he was there, he invited me, and I don't know how, at the end of my PhD, I found something for a short visit, and 1 year later, in 1998, I stepped up here for the first time, and we were in Corcovado together. So, of course, we sometimes went to CBPF also. So this is our first joint paper at that. No, it's 1 year later, but we did the things here together with Marcelo also. At that time, we were not see each other yet, right? So very good. Then after this, of course, we have discussed many things. And there, once we were in the restaurant of CBPF, he told me that, look, Uğur, if you continue your career in statistical physics, surely you will not be rich, but I assure you that you will enjoy it. So I thought, well, maybe he's a good guy, etc. So then I was not very keen on having money. So then I immediately, Constantino immediately offered me a postdoc position after my PhD. I also found some money from TÜBİTAK, and I end up in a one-year postdoc here. As you see, Aglaé, Constantino, in Constantino's room, I think, over there. And I started to enjoy life over there. Well, after finishing my postdoc there, I just returned İzmir'e, my university, Ege University at that time. But since then, we keep on collaborating without any interruption. So just 1 year later, you see our unforgettable Bilisimus conference over there. You see, believe it or not, this is me, and this is Ernesto. Ernesto somewhere there. Constantino is like today, as you see. Then Constantino became 60, and we were in Angro dos Reis. You see, Andre is here, and believe it or not, this is Emmanuel. Now he's that much. So then several conferences, of course. So I just picked some of them because of the time. You see our famous Erice meetings over there, and also Kyoto was very nice, although it's not very warm over there, but anyway. So more conferences, for example, StatFis was very nice, together with the Catania meeting, right? Here you see Latin American workshop of nonlinear physics in Buzios. You see one of the giants, Christian, also over there, Stefan, who are absent today. Well, you guessed that sometimes we were working very hard. You see here the famous Trieste conference. So I and Ernesto, we were hopelessly trying to discuss something, and he's laughing, you see. So, of course, the hard times like this, of course, not only in those days we were just young, but also very recently, as we are getting older. For example, this is just last year here in CBPF. We are working, you see, still. Yeah, you see one of our figures here. So we are really working over there. But there are even other difficult times that we were even working harder. You see how Constantino is eager to teach Parisi Sirtaki. You see how he has talent. On the other hand, Parisi is hopeless. You see? No. Clear. Sirtaki, esse Sirtaki. So, well, Constantino is always like this. So even harder times he had. You see, during the Greek-Turkish conference that we were organizing 3 times, I think, in Turunç, Marmaris, Turkey, and also Greek islands like Rhodos, Simi, just like this. And Constantino is even working harder, as you see here, over there. Even exceptionally harder we are working. As you see here, this is the 2015 event here, and this is Kaisaras, and we are discussing very important things over there. And here, Erice, you see Ernesto, Constantino, and Evaldo here. So I don't know what we are doing over there, but anyway, so of course, during the time we arrived to 2013, most of you should have remembered it, right? Almost the same community here, 70th birthday. It was. Then, of course, we realized that we are getting older now and decided to work even harder because time goes by. And you see Pizza Brass in Lagoa. So we are discussing about important projects over there. Denise appeared here, therefore you see Ernesto, Pilastino Filio, Roseli, Enzo. So also in Turkey, Turkish Physical Society meetings, Constantino was having some hard times during the cocktail, and they organized some kind of music, even samba, for him to dance. And finally, at the end of the conference, I just recognized that several girls are coming to Constantino, approaching, and let's dance together, because he's like this. Here you have Istanbul also, with the rector and vice rector of one of the universities over there, and like this. And believe it or not, we are working even harder in, for example, Chios. You see how it's very hot, so it's very difficult to work. Grand Pazar, Istanbul, he's still looking for some carpets, etc. And finally here, remember, Evaldo, this is Sekudia. So it's very heavy during the lunch. After the lunch, they're just serving this. The Greek guys are very like this, like Turkish guys. So it's very well. It's like cachaça. Very good. So, but don't think, of course, that we are just workaholic. We are also very good in sports. So you see here, Constantino is just like artillero, atacante. You see, year unknown, but I don't know. So you see here, we are also having some exercise together. And also here, you see, Foz do Iguaçu in that conference, but we are approaching to the rainfall, etc. So very good. So and finally, it was yesterday. We were in Lagoa, and we have celebrating his 80th anniversary, and most of the family is here. Very good. So, and if I come back to my first slide, remember this, and he told me that in those days, 1997, he told me, if you continue your career in statistical physics, you're not going to be rich for sure, but I would assure you that you will enjoy it. And after 26 years with 20 papers, well, yes, Constantino, once again, you are right. We really enjoyed our lives as you promised. It was really a pleasure and privilege for me to work together during these years. Obrigado.
Thank you very much, Hugo, for the pictures, for the history part also, besides the physics part, and the comments, photos about the hard work.
Ernesto is working very hard.
Yeah. Where is he? A completely different guy, you see? Do you know him? This is the third version of Ernesto.
Yeah.
Okay, thank you very much. So let us go to the coffee break. So let us start with Walter Silva. Talk to us. Please, Walter.
Okay. Good afternoon, everyone. My name is Walter Carvalho Silva. I'm from Goiás State University in the Midwest of Brazil, in the state of Goiás. And thank you, the organizing committee, to invite me. It's a great honor to be here celebrating the 80th of the Professor Constantino with many experts in thermostatistics. It's scary for me as a chemist, so have a patience with me, please. It's a great moment for me to be here because my entirely research field in the last 10 years is inspired for the Professor Constantino. These ideas of the Professor Constantino was introduced for me by my advisor, Professor Kleber Mundin, to apply in problems of the chemical kinetics. So initially, I will introduce some basic concepts in chemical kinetics, how we can use the ideas of the Professor Constantino to understand a specific case in chemical kinetics. So when I told you about chemical kinetics, I working with a specific reaction. Where a specific reaction, I suppose that I have reactants forming products with breaking and forming of the bonds. So to understand the temporal evolution of the concentration of these reactants, Boltzmann has proposed this differential equation, where it depends of a kappa, a parameter kappa, the reaction rate constant, and rho, a Greek letter, which is connected with the mechanism in a specific chemical reaction. So if I suppose, if I modulate this rho with 0, 1, E2, this process is very common in pharmaceutical industry to analyze drug degradations. I can perform interesting scaling. It describes the mechanism for the system. For example, here I used the data of my coworkers about the respiration of the leaves, where we analyzing the consumption of the oxygen, the molecular oxygen, as function of the time, and we observe that a linearization is obtained when I suppose rho equals 0. Okay, this is a classical procedure in chemical kinetics. This is the basic of the chemical kinetics. But an important variable in chemical kinetics is the reaction rate constant, because it's temperature dependent. And Van 't Hoff has proposed that this dependence is an exponential function. Van 't Hoff has proposed this exponential function with dependence of the two parameters, A and activation energy. But only Arrhenius, your postdoc student, has interpreted this activation energy. And we can observe that I assume a scaled Arrhenius plot as the log of kappa and the reciprocal of the temperature, we can obtain a linearization. And this linearization permits I quantify the activation energy of the system. Activation energy, I suppose here as this Arrhenius interpretation, as energy necessary to a reaction proceed. So, if I'm sorry. If I propose a Arrhenius plot as a log of kappa as function the inverse of the temperature, I suppose a linearization, but with the advance of the experimental techniques, it's possible to identify strong curvatures in the Arrhenius plot. How we can describe this behavior? We try analyze this type of the behavior in the literature. We found in a plethora of the fields, several examples of the curvature. Look here, for example, in the astrochemistry, in problems of the astrochemistry, this is a Arrhenius plot, a strong curvature. This is not described by an exponential function. Here in catalysis, in problems of the enzymatic catalysis, we have a change of the curvature. This is very interesting. Of course, the classical problem of the curvature is the temperature dependence of transport properties in glass formation. I'm sorry, but a problem here. In 2010, Professor Mundin and Professor Aquilante has used the idea of the Tsallis statistic to replace the exponential in the Arrhenius function, to describe these curvatures. Here, they consider that a simplification that the Q minus 1 can be replaced by a parameter D. It's the same correlate. They are correlated. So with this description, we can identify two types of the curvatures, a concave curvature and a convex curvature. And this parameter, the Q, can modulate uniformly this behavior, sub and super, uniformly. When Q tends to 1, D tends to 0, of course, we recover a Arrhenius model. And it's very interesting that when I start to work with Professor Mundin and Professor Aquilante, we calculate the activation energy of this model using this definition. This is definition using proposed by the UPAC, And you observe when I assume the inverse of the activation energy, I have a linearization of the problem. The inverse of the activation energy by the inverse of the temperature, I linearize the Tsallis statistic. It's interesting here that the subarrhenius problem are connected with quantum tunneling elementary chemical reaction, and subarrhenius are connected with collectivity problems. Uniformly, I can describe the subarrhenius when D is negative and superarrhenius when D is positive. This is very interesting. And exactly 10 years ago, we have proposed a meaning for the Q of the Q, of course, of D for case of the subarrhenius under quantum tunneling, which we can describe this deformation parameter as depending from the frequency of the crossing through barrier, and the height of the barrier. This result was very interesting as a predictivity model. So, with this power law, we try to study the origin of this power law. We found interesting paper from Boltzmann and Maxwell before they proposed the idea of the entropy. In here, they used this idea of the power law, but they assumed the thermodynamic limit. When they assume the thermodynamic limit, they recover, of course, the Boltzmann distribution. This same idea was used by the great researcher in chemical kinetics. For example, Professor Isherwood is a great number in chemical kinetics, and he provides an interesting discussion about this power law to describe chemical kinetic process. Another Bible in chemical kinetics is the theory of the rate process due to Professor Eyring, and again, they assume this power law, but they assume the thermodynamic limits. So, for us, the thermodynamic limit is not important because the thermodynamic limit is not important, it's hard. It's not appropriate in this description because the Avogadro number is not our focus. Our our focus are the number of the collision in a process. And the number of collision in a process I can obtain by the iron number. Observe the difference of this number, 10 to 24, 10 to 13. Consequently, we have a relaxation of the thermodynamic limit. You can suppose here, this is our proposed, a Kinect limit where the statistic of the Tsallis can recover or the Boltzmann without consider the thermodynamic limit, and we can obtain in the limit, of course, conditions for super and subarrhenius behavior. Okay, with all this idea, with all this number of the experimental data and description, we try to analyze the importance of the inverse of the activation energy, because the inverse of the activation energy can be linearized related to Tsallis statistics. So we imagine that this variable is important. Look here. We observe analogous function to inverse of the activation energy in a paper of the Soulitier applying in spin glasses. He used this idea to linearize the temperature dependence of the transport properties in glass transition in a spin glass, and compared his model com a classical model in condensed matter science, the Vogel-Fokker-Taumann model. In 90 decades, Stickel have used this idea to numerically calculate numerically these derivatives, this differentiation. Here he can obtain a certain level of the linearization as the inverse of the apparent activation energy, not necessarily the same. This information is very impressive for us. I read in the paper, the germinal paper of the Professor Wilson to studying critical phenomena. He proposed exactly a functional form of the inverse deactivation energy as an important function in process of the renormalization. And he supposed that around the critical region, the linearization is very important. In the quantum of the theory of the fields, there is an interesting, there is an analog equation at the beta function, or a type of the Kalan-Szymanski equation, with the same characteristic of the inverse of the activation energy. So we proposed the inverse of the activation energy to treat problems in rate process, chemical reaction, in charge transfer, momentum transfer, several possibilities. And we suppose that the transitivity here, we define it with a gamma Greek letter. And we suppose that can be written as a power loss series. And of course, if I assume a first order correction, I linearize the equation. And then if I solve the differential equations, I recover the Arrhenius, the Tsallis statistic. Applying the similar protocol supposed by Stickel, we calculate numerically the transitivity for a series of the problems in glass transition, in biological process, and geological process, several types in chemical reaction. And you observe ours an interesting range of the temperature that the linearization is preserved. This is very interesting. Here another several examples in range, in important realistic range of the temperatures for chemical reactions, transport of other in the DNA, and look, that's interesting. These are the data used by Arrhenius to propose the Arrhenius law, and the Arrhenius law is not Arrhenius law, it's Tsallis law. Is a Tsallis statistic. I I analyze this data. If Arrhenius' law was correct, the transitivity should be constant. It's not constant, it's a linearized. So we proposed a transitivity plane because we can compact all this process just in one plane. Of course, in important range of temperature, we have linearization for sub-Arrhenius. In this case, is sub-Arrhenius. In this case, we have super Arrhenius, but in extremely conditions, also in the transitivity plane, we observe deviation from the linearization. So we can, unfortunately, we can propose a generalization of all this process with this equation, the transitivity, where I have three parameters, only three parameters, I can compact everything. The size of the barrier, the area of the barrier. Here we define a depth energy, and we propose a universality class exponent. Why? When this exponent equals 0, we recover Arrhenius or Boltzmann distribution. Zeta 1, deformed Arrhenius or Tsallis distribution. And of course, very interesting here, that zeta is equal to, we have the Vogel-Foucault-Tauman. Impressive, this result. So if our proposal here, look, if our proposal is consistent, when I propose a renormalization of this function, I have a loss of dimensionality in the epsilon and the abscissa x and here. We have again a linearization. I just used a little data because this data obtained by a group of the Professor Aquilante is exactly solved for extreme ultra low temperature. So I have no noise to perform the numerical differentiation. I'm trying to apply this procedure in several other examples. With this set of tools, we can perform a series of the application. And the useful application is the description of the reaction rate constant proposed by Van 't Hoff, the temperature dependence of the reaction rate constant, which can be described by a traditional formulation in chemical kinetics. In chemical kinetics, the transition state field. The transition state field assume the partition function of the reactants of the activated system and calculate the partition function of this molecular system. However, here we have a Boltzmann distribution. It's based in the Boltzmann distribution. So, since delinearization is important, I can replace this exponential function by the Tsallis distribution. And of course, I can use the interpretation for the deformed parameter or Q parameter to estimate the reaction rate constant. When we apply this type of the formulation in several chemical reactions, we obtain a high level of the agreement with the experiments. Look here, we apply in several reactions, several reactions, and more recently, we have applying this formulation in environmental problems related to mitigate organic contaminants. It's a classical problem of the stability of the degradation. Here is the super Arrhenius behavior. Is a topic understood, is not published. We have selected a series of the temperature dependence of a series of the transport data. Try to connect the empirical parameters of the D Arrhenius with parameters of the glass transition. Using the idea the idea of the transitivity, we can observe that the linearization is very good. So we fit this data, consider this linearization in the transitivity plot. We can connect this empirical parameter with glass transition temperature and the heat capacity in the glass transition temperature, and propose another interpretation for the Q parameter for superahenos. This is under, as I told you, this is understood. Another interesting formulation, another interesting example is not necessarily a curvature, but a change of the curvature. This is the same problem identified by Arrhenius, but Arrhenius avoid working this problem. He just work in the linear part. That's not exactly linear. But very recently, this problem was treated by macromolecular rate theory, where they propose a correction in the transition state theory, consider, look here, a correction in the heat capacity for the proteins. They assume that the main hypothesis here is that the heat capacity between the activated complex and the initial state are constant. However, this formulation does not consider an important paper in the 30th decade, interpretation of the Lamer for the activation energy in chemical, for the activation heat capacity in chemical kinetics. Look that this definition is exactly the mathematical definition of the curvature. The second derivative is the definition of the curvature, is our problem. So I got the exact data of the Arrhenius. This is the exact data published by Arrhenius. Look, it's a curvature, but Arrhenius only work with this part. And I numerically calculate the activation energy and the activation heat capacity. It is not constant. So this model can be completed because it supposes that the activation heat capacity is constant, is not constant, is a temperature dependence here. So here is a perspective. We are expanding this idea of the activation heat capacity based on the Lamer's interpretation. And we assume that the idea of the Lamer, that a difference between the activated complex in the initial system, but I assume a supermodel. This supermodel can be a great molecule forming a bond with another great molecule. But I will consider just a specific degree of the freedom. For example, in this system, I can just consider the translational contributions. When I form a bond, I will consider vibration and rotational contributions, applying this idea, de Lamer, using our differential equations based in linearization of the transitivity, of course, the Tsallis distribution. I can generalize sub and super Arrhenius, the interpretation for sub Arrhenius. Look that if I consider a majority, the vibrational contributions I recover is for first principle, it's not phenomenologically. I recover the sub-Arrhenius model. Remember this equation. And if Professor Constantino permit me, a simple gift, because I proposed this idea in 2013, 10 years ago, exactly 10 years ago. And this year we can propose with the case for super-Arrhenius is understood this interpretation, but I imagine that can be applied in elementary chemical reaction under super-Arrhenius regime. Sorry. Yes, because uniformly you can describe subarrhenius when D is negative and superarrhenius when this is positive, is consistent. Negative for sub and positive for super. It's consistent with the idea. Exactly. Yes. D here is Q minus 1. It's the same interpretation. So my acknowledgement are important persons that help me so much to understand these problems. First, my PhD advisor, the Professor Kleber Mundin, that introduced now this idea. And after the Professor Aquilante, Professor Aquilante has helped me understand the several details in theory in chemical kinetics. And a Professor Nayara has helped me to analyze a series of the data, interpret and discuss several data. And of course, agencies that support me. Here, a picture, Professor Constantino. It was the first time that I met the Professor Constantino in a conference in Accademia dell'Ince in Roma, organized by the Professor Aquilante and of course the Professor Ernesto. Of course, the Professor, also Professor Ernesto. And in the last year, kindly, the Professor Constantino visited us in Goiás, in Pirinópolis, a touristic city in Goiás, in a symposium of theoretical chemistry. Here, Professor Constantino, Professor Kleber, young persons, young research here. So, Professor Constantino, I thank you again for your great contribution in my field of the research. I'm sure that your ideas has performed a transformation in the science of the Goiás, specifically in the chemistry. I thank you very much for your contribution. Thank you.
Thank you. Thank you for your nice talk. Questions?
It's a very nice talk. I like chemistry also. Oh, there is one interesting challenge in biophysics. That is the Levinthal paradox. When you have the protein folding, it's an open question. How many states you can get before the protein folding results in a harmony or some different kinds of structure. You brought in the equation, the last equation, using the angle, right? Because it's not in the
rotational
the rotational, yeah.
temperature.
So it's interesting approach because I never saw this kind of parameter dependence, and I think this is related with also the protein folding if you apply it for the analysis.
This is new. This is new.
Because you know when you see the Arrhenius plot, I think we have a different Arrhenius plot for each kind of protein structure, right?
For protein fold,
right?
Super Arrhenius behavior.
Super Arrhenius,
Exactly.
right? So it'll be interesting to apply this kind of parameterization to understand the protein folding in the framework of Levinthal paradox.
Yes.
I never saw that, so it's an interesting application to bring it to.
Okay, thank you very much.
To your theory.
Thank you very much.
Some other question? So where?
When you use this approach, you interpret, the interpretation is there are few particles in the reaction, so it's like a small region. So you use Tsallis statistics, is this?
No, I suppose a microcanonical description. And I suppose that I have initial conditions, the reactants, and an activated system. So using electronic structure method, for example, DFT, density function theory, I can estimate several properties. After estimate these properties, I can use this property and apply a canonical idea. What's the canonical idea? Is the Tsallis distribution.
Understand.
Because when we work with chemical kinetics, we work initially we work with microcanonical idea, but it's necessary to perform an average in the temperature. When we perform the average in the temperature, emerge the Tsallis statistic to describe these deviations.
So let us think again, Walter. And now the next talker is Ernesto Borges.
Okay. And I'm sorry to disappoint you. I won't show any photos. Where's the? Here. So the title of the talk, Nonlinear Dynamical Systems, Time Reversibility versus Sensitivity to the Initial Conditions. This is a work, a recent work with Constantino. And, but first, as many did, I will divide my talk in two pieces. And the first, I will make a rapid retrospect of previous works. And then I show this one. I first met Constantino at, let me check, almost exactly 30 years and a half ago. And he gave a talk in Salvador. Salvador was the first capital of Brazil, where I am from. And the title of the talk was Generalized Thermodynamics. And at that time, I decided that I would like to get into this field. And a few years later, I became his PhD supervisor. He became my PhD supervisor. And well, since then we are working, and I have benefit of the workings, and of course, and mainly, principally, of his friendship. And some previous collaborations. We have different areas. I put here on low dimensional dynamical systems because it is related to the main topic of the talk. And the central idea would be the quest for understanding the family of Q indices. And many of you, almost all of you know, there is an index that characterizes the entropy production rate, the finite entropy production rate, the Q entropy. There is another index that characterizes sensitivity to the initial conditions, following on a Q exponential law, and a process of relaxation characterized by a different index, and stationary distributions that characterized by Q Gaussians or Q exponential related functions. This work here was the first we made on this topic, and with together also with Garin Anyanos, that was a PhD student at that time, and here Paulo Murillo. Tomorrow there will be a section in honor of him. So it was a fortunate coincidence that I have his name here. And this one is the logistic map, more generally the Z logistic map. And we have basically studied two aspects of this map. The Q sensitivity, I won't go into the details. Many of you know that. But there is the index that characterizes the sensitivity to the initial conditions, and relaxation to the final attractor. And I put here some figures for the problem. And this one is the one example. If C equals 2, because the original logistic map, with this control parameter R equals 2, that is fully chaotic conditions. And we see here the Boltzmann entropy, Boltzmann-Gibbs entropy. And at the Feigenbaum point, we see a maximum, and then it goes to the final attractor from above. And here is a figure that shows the relation between Q sensitivity and the Q relaxation. Q relaxation depending on the graining of the system. Cool. There's other paper together with Guiomar Ruiz, that is here, and Ugur Ternakli. Yes, here. We studied the standard map and made a statistical characterization of the standard map, and we analyzed the Q entropy, the Q entropy value, the Q sensitivity value here, and they are equal following the generalized Bayesian identity. Well, the generalized Bayesian identity was shown before. We analyzed that this specific example. We analyzed the rate of relaxation, also of this problem with this index here, Q relaxation, and the statistical distribution. It's a linear combination between a Q Gaussian and a normal Gaussian, with this value of Q that this one. And also, we made the same people, Guiomar, Ugur, myself, and Constantino. We studied the web map, a different web dynamical system. And we also analyzed the same, not the same, but these indexes. Q entropy, Q sensitivity, and the Q stationary value. I won't go into the details of those figures, they are just to complete the scheme. And this one, a recent one, together with Angel Ricardo Plastino, and we analyzed multidimensional systems. Multidimensional systems. We coupled, we considered, in this case, two-dimensional Z logistic maps. In this case, this zeta here is the same as the Z before, in 2 dimensions, and the objective of this paper was to verify this conjecture, of course, made by Constantino, that the Q entropy index of a multidimensional system may be found between the Q and entropy index for the one-dimensional systems for fully independent dynamical variables. In this paper, there is also the 3-dimensional case, but I didn't put it here. Those are the figures, and we see here the entropy increasing in time. This is the one-dimensional case, so is the ordinary one. The new one is this, the 2-dimensional case, and the proper value of Q that originates a linear growth of entropy, in this case, is this value here that coincides with that conjecture. This example here is for Z equals 2, the original logistic map. And this example here, there are 2 maps. These 2 are both with Z equals 2. And this one Z equals 2 and Z equals 3. So that conjecture is verified within the numerical errors. And we also have this recent work in which we analyzed the overshooting of the entropy. This is known since long, but we performed a scaling of the maximum here, and the scaling of the final values. Well, of course we tried, but we could not find a unique scaling for for both of the situations. Well, and now we come to the central point of my talk. And if you consider a time series with a number of values, and this is a proposal to split the time series into 2 series, one symmetrical and the other one anti-symmetrical, with respect to time reversal. So this one is, the symmetrical series is xt plus x final time minus t divided by 2. And this one is the anti-symmetrical series. If you sum both of them, you will recover the original time series. And I put here an example for with the logistic map. The logistic map. So I consider here one initial condition, 0.1, and one arbitrary number, and this final time, 2000. This one is the time series, the original data. And the black dots are A equals to the strongly chaotic case. And the red dots are at the Feigenbaum point. So we have weakly chaotic, the weakly chaotic case. We have this pattern. This one is the same as the first one, but in reverse time. So the abscissa here is TF minus T. Well, these two plots in the bottom plots, this one is the symmetric series. And we see the black points dispersed all around the phase space. And this one is the antisymmetric series. And what calls attention is the red points, they are concentrated near zero. That reminds us possible time reversibility for this system, or at least quasi-reversibility for the system. These two plots are similar to the previous one. Let me show you this one. So, but this is the final time 2000. This we have the red dots, the final time 2000, green 2001, blue 2002, 2003. So this shows that the final time plays an important role in this method. And those points there were concentrated around zero in this antisymmetrical plot. You see that they are not around zero anymore. So the final time is important for this. I pressed the wrong. And this one, we show the influence of the parameter, the control parameter, A. So in this plot, the Feigenbaum point is the black points, they are here, around zero. And the blue dots are A equals 2, the one that previously appeared, spread over the entire phase space. And there are two instances here, A equals 1.5 and 1.6. And the red and green dots, they spread in the phase space. But what calls attention here is they spread continuously. So when you go to the Feigenbaum point, to the completely chaotic system, the points are spreading continuously and not suddenly, as perhaps we first expected it to happen. Because those points here should be strong chaos and not weak chaos. Yeah. Yes. Here we see the influence of the control parameter on the averages. We see here the bottom plot. This is the average of the symmetric series and the average of the antisymmetric series. We see here the parameter E from 0 to 2, the value of the mean value of S and A. You see the mean value of A is near zero almost always, and there are fluctuations. And these fluctuations coincide with the values of A, for which the Lyapunov is 0. This one. These are the standard deviations of the symmetric series and antisymmetric series. For we have here different initial conditions with the same final time. And what happens here? This one is this part of the graph is the order region, and let's see this one, the antisymmetrical region. We see they more or less coincide, but if you see here, it's difficult to point of this. If you see here, we see two branches. They come together, more or less. But here they divide into parts. This is the cycle 2 part of the logistic map. And if you look closer, there is one part that there are 4 values of the standard map coinciding with the cycle 4, and so on. And at above the Feigenbaum point, they are more or less the same. And this one is the influence of the final time. This one perhaps is better to see. We see here the cycle 2. You can see here cycle 4, the same in the anti-symmetric series. The figure is not, the resolution of the figure is not sufficient to see cycle 8, etc., but it should be there. And this is another curious behavior of the standard deviation. You see that this part here, there are black dots and green dots. The black dots are the standard deviation of the symmetric series for the time 2000. And the green dots that are superposed are the standard deviation of the anti-symmetrical series for a different final time. So there is this curiosity. These two coincide. These two coincide. One of these curves is the standard deviation of symmetric, and the other the anti-symmetric for different times. You see, this is the cycle 2. So if you look in the cycle 4, would be a similar behavior. Well, this is the one instance of the possible use of these methods. And here I show another instance. It's a very preliminary results of sunspots. So Galileo discovered that the sun has spots, and there are regions of intense magnetic field that changes the convection zones. So the temperature of those regions are lower than the rest of the sun. So the average temperature is around 6,000 degrees, and this region is around 3,000 degrees. So by contrast, we see them dark. And these sunspots, they are registered since long. And we have here, I took the data from this site, and from 1818 up to 220, and they have the data of the number of sunspots at each 8 hours, almost every day. Well, almost in the recent years every day, but in around the beginning, it's not exactly every day, but, and this is the number of sunspots, and it is known a cycle of these sunspots of around 11 years. And people who work in this, they identified these cycles. So we have this figure here. You can see the different cycles from cycle 7 to cycle 24. Cycle 24 was the last cycle that finished in 219. So I applied that method, the symmetric series and anti-symmetric series. This one is for the cycle 24 that coincidentally, it has this, the period of 11 years because the period is around 11 years, not exactly. The last one was practically 11 years. And this is the symmetric series. And the red curve, I put a this function, sin square, and this function, there is no fitting parameter here because the period is given and the amplitude I calculated by the average value of the square of the data. And visually, I would say it's not that bad. This is the symmetrical series. And this is the anti-symmetrical series of the cycle 24. And here I put the sine function to the cube power. And more or less, as I told, this is a preliminary study. I'm also trying different powers, odd powers and even powers for each case that may improve each case, the case. But perhaps this approach may have some insight or may extract some information from this data. And finally, happy birthday, Constantino.
Thank you, Ernesto. Question?
Very nice, Ernesto. I have a question. Why you think this 2000 time is so important? I think you chose by chance.
There's nothing special in the number 2000. We choose that number just to avoid an excessive number of points to see in a graph. But what is important is the following: 2000, 2001, and 2 and 3, they change. And so in order to identify this, the symmetric or anti-symmetric behavior of a time series, you have to choose properly the window in which you see. In the sun spot problem, this was previously done because the researchers, they identify the cycles. So the cycles, since they are identified, cycle 7, 8, etc., the initial and final time was more or less defined.
But in the sun, you know that it's periodic, but in the logistic map, you don't know exactly. Of course, there is the recurrence time, Poincaré time, and also for chaotic systems, there is a recurrence time. So you can imagine that if you are at the edge of chaos, it could be even more. So that could be a possibility. But for some reason, 2000 has some importance for the logistic map.
Yeah. I would think in a general case, you must choose a final time, and then vary this time, and perhaps you find one for which the anti-symmetric series is close to 0. So that if you change this, you may find
Okay, I have a double question concerning the sunspots. You presented, I guess, the last cycle, but you had several before. Have you done the same adjustment for
yes, yes. I showed this because this one was one example with the period is 11 years old, 11 years. And I have made also other cycles, but not all, because as I told, these are preliminary results, but the pattern is
and the A values that you're using for the adjustment, that is a variation because that depends on the amplitude, right? It's not always the same.
Yes, yes, they change from one cycle to another. Yes.
And then the other question is concerning the data itself. You said that they are registered every 8 hours.
Yes.
And then my question is how this is done over the earth, because
yeah, because
you need to go around.
Yes, yes,
and then
of course.
It could be cloud.
Because they collect from different observatories. It's not just one. And I don't know exactly the procedure they do. I don't know the procedure, but they collect different data. And this one was the processed results.
Question, Reinaldo.
Okay, as we kick off the Sunspot program, it's very interesting to compare the patterns among all cycles, especially for the minimum Maunder minimum of Maunder. You know, there is a minimum that's probably the explanation for that is a kind of stellar evolution phase transition that time when the sun. So I think the asymmetric pattern for especially comparing the minimum Maunder with the other cycles will be a very interesting result. Just a suggestion.
Okay, thank you.
Any other question? Okay.
Just curiosity, how come this 11 years, is there any physical mechanism? No?
I don't know. Solar dynamics.
There are many magnetic stars that the range for the toroidal configuration to the toroidal one. If you go to the stars at the same age of the sun, around 5 billion years old.
You get a range of from 10 to 30 years in this total cycle. It depends on the size of the star, the age of the star, okay, and some other parameters like the magnetization, how magnetized is the star in that age where we are observing them. So that's the dynamo. The input for the dynamo are the age, size, mass, and also the magnetic field.
Nuclear reaction? It's a carbon?
Yes.
Yeah. The helium burning, yeah? Yes.
Thank you. Let us thank again Ernesto. So let us go to our last talk, Roseli, before the hard work.
Can you hear me? It's okay? Okay. Okay. So I want to thank the organizers for scheduling my talk and organizing this very nice meeting where we meet with friends. So, okay, can you hear me now? Okay, good. Okay. So I want to thank the organizers for scheduling my talk and accepting my registration, and also for organizing this very nice meeting where we can meet all friends and celebrate Constantino's birthday together. It's very nice to meet everyone again. And today I'm going to present this talk on a neural network model for associative memory based on multidimensional neurons. And this is work with Ángel Plastino, who is here also from Argentina, from Universidad Nacional del Noroeste de la Provincia de Buenos Aires. And I think I'm going to talk about Constantino during my talk. I'm not going to separate. And I also don't have any pictures. But I think it will be clear importance of Constantino, not only Constantino, but many people in the community that have contributed to things I've been doing. So I'm very happy to be here. Yeah. And well, I start with my motivations. And initially, I started working with the Hopfield associative memory model. It has been used to represent an approximation of human memory functioning, and also as an artificial storage device. And these neural networks they consist of dissipative units, the neurons. In the case of artificial devices, we call them units. In the case of neuroscience, we call them neurons. And an important property is that these units interact in such a way that the network admits a global energy or a Lyapunov function, and the dynamics of the network works in such a way that the system goes downhill in the energy landscape. And okay, in most of the models for associative memory, the individual neurons are described by one-dimensional variables or dynamical systems. And the capacity of human memory to store and retrieve information is very central to many mental processes, whether they are normal, pathological, or when we talk about consciousness, unconsciousness, memory is always there. So these have been widely studied by psychiatry, psychoanalysis, neuroscience, computational science, and even other fields. And in recent years, well, not so recent anymore, but a few decades, I've been working with many colleagues in developing schematic simulation models based on this associative memory that represent aspects of some mental processes as described by psychoanalysis. And by mental processes, I mean neurosis, creativity, delusions, interaction between conscious and unconscious phenomena, and things like that. And maybe here is where Constantino has been very important for me. It's because this sounds very eccentric, right? When we talk about modeling neurosis and things like that. And I remember when I met Constantino, I was first reading some of Freud's description of these mental processes, and we had the idea that what Freud described as neurosis was actually what we treat in neural network modeling as associative memory. And it seemed a bit eccentric and weird at the time. And Constantino was one of the first people to hear me talk about this. And he was very open-minded and welcomed the ideas we were having. And that's why I joined this community. So I have much to thank Constantino for everything I've done, both directly, because in many of our works, he has given us very good ideas. He has been very supportive also with the work we do at our university, during these decades, we created our graduate program. Constantino has been on committees for evaluating students, and it's been very important for me and also the place where I work. And with Constantino came a lot of other people, you know, like Evaldo and Angel and Ugur, Ernesto, and everyone contributed in Luciano, everybody. Everyone contributed in some way to the ideas that we have been working on. So this is, and in my case, there is this very, this issue regarding a subject that seems, that's not very well defined or well accepted by the scientific community in general. It's a very, sometimes to many people, it sounds very weird, right? So it's important to have had the support for what we were able to do. And we have used also these Hopfield-like networks and the generalizations, such as the Boltzmann machine. And here we have used the generalized statistics, thermostatistics. And there is a paper by Constantino and Daniel Stariolo. I think he's not here today. Where is Daniel is here? No, yeah. And I will say that maybe I'm probably one of the people who most cites this paper, because I cited it in a lot of my papers, because we used it and we had some very interesting results with the generalized machine and in quite a few of our papers. And most of the fundamental models in theoretical biology exhibit a dynamics that is dissipative. And important examples are the Lotka-Volterra models in biological population dynamics, the continuous Hopfield neural network models, the Cohen-Grossberg network models, which actually are just more general than the Hopfield, and various mathematical models for biological evolutionary processes. And all biologically inspired models supporting universe computation are also non-conservative, and in the case of discrete models, non-reversible, and they exhibit modular structure consisting of interacting units with intrinsic dissipative dynamics. So the contribution, so today I'm just going to present a small step in the context of this work that I just described. And it seems that it's possible that to represent the complexity of real biological neurons, it may be, we may need to describe them as dynamical systems with more than one dimension. And so in this work, we did a mathematical treatment of how we can represent multidimensional systems. So we extend the structural description of associative memory neural networks to more general scenarios, and we formulate a family of neural network models with interacting dissipative, interacting dissipative multidimensional neurons encompassing other biological models with non-conservative dynamics. And these models that we show here today, they generate dynamical features which are similar to or akin to those required when we model associative memory. So we obtain many of the properties that are desired in associative memory networks. And here is some related work that we found, treating also multidimensional neuronal systems. And for our model, it's a continuous associative memory neural network with n multidimensional neurons. Each neuron is modeled as an n-dimensional descriptive dynamical system. The states of the neuron are given by a vector. Now, in the usual Hopfield model, this is just a scalar quantity. And each neuron may have a different, be described by different dimensional vector. And we need two scalar functions and two vector functions associated with each neuron. And these functions are related to the intrinsic dynamics of the neuron and with the output signal through which it affects the dynamics of other neurons. And we use also a positive definite symmetric matrix, which is related to these functions and by these relations here, okay? So the independent functions are these, and the B and the M are derived from those. And then we have this Jacobian matrix associated with the function D. And oops, I'm still a bit, okay, here. And the positive definite character of this matrix gives us this inequality for any vector V. The interactions between the neurons are represented or coded in a matrix, array, where each element of the matrix, CIK, describes the interaction between two neurons. And the elements of this matrix, I'm sorry, just a second. And each element of this array is also a matrix. And the elements of these CIK are constant and don't depend on the neuron state. So, and we have this relation here that describes a symmetry in the interactions. So the dynamics of a single neuron is governed by an equation of motion like this that depends on the potential. Sorry, I'm a bit lost with this. This potential plays the role of a potential energy or a Lyapunov function. And when we take the time derivative of the potential and substitute the equation of motion, we get this relation. And since A is positive and M is positive definite, then we see that as the neuron evolves according to its dynamics, the potential energy decreases, which is desired in associative memory models. So that an isolated neuron always evolves downhill in the potential energy, multidimensional landscape. And the vector, the derivative of the state has a negative projection on the potential, on the gradient of the potential. So now we don't want to treat single neurons. We want a network of interacting neurons. So in the equation that describes the dynamics of the network, we have to have another term describing the interactions between the neurons. And the first term here corresponds to the intrinsic dynamics of the ith neuron, and the second describes the effects of the other neurons on the dynamics of I. And the strengths of the interactions between the neurons are given by this matrix CIK. Okay. Just to remember that in the case of the Hopfield model, it's here we have just a single coefficient, okay? And okay. Now, we want to show that this formulation of the dynamic allows for the definition of a Lyapunov function. And so we have this function where this term is associated with the intrinsic dynamics of the neuron, and this term is related to the interaction. And if we take the time derivative here, we get an expression like this. And when we substitute the evolution equation for the dynamics of the neuron, then, we obtain this expression. And if we use the definition, the functions B and the matrix M that we defined previously in a relation with the potential, we can rewrite this in this form. Okay, and we want to prove that this derivative is negative so that the system evolves downhill in this Lyapunov function when it follows its dynamics. So here we have to calculate still the derivative of this function and the time derivative, and it has this form here, and we find the transpose here, which is what appears in this expression. And this here is the Jacobian matrix that we showed previously, equation 3. And then using the relation between the Jacobian and the M matrix, we can rewrite this time derivative in this way and substitute this in the previous relation, and we obtain this new expression for the time derivative of the Lyapunov function. And we can rewrite that if we use define this vector v. We can rewrite the previous expression in this way, and since the AI and MI is positive definite, then we see that this is negative as is desired of an associative memory model. So we have a network model that is multidimensional. It exhibits a dynamics admitting an energy, a Lyapunov function, it's the inverse of the matrix. Yeah. Yeah, it's -1. Yeah, it's -1. Yeah, it's a typo. I'm sorry. Yeah. Okay, so it exhibits. It's okay. Yeah. Okay. So we have an energy, dynamics emitting an energy, a Lyapunov function omega, and it has two terms. One inherited from the gradient-like character of the neurons' intrinsic deceptive dynamics, and one arising from the interactions. And the system always evolves downhill in the energy landscape, tending to the landscape's local minima. And in this model, we represent the interactions between all the possible state variables representing the system. Right. And then I think just to make things look a bit more familiar, it's nice to see the connection of our model with the Cohen-Grossberg and the Hochfeld model. If we take, the neural network models proposed by Cohen and Grossberg in this paper, is an important paper in associative memory neural network literature. They constitute a particular instance of general models described by our equations. If we take the case where we have one dimension, And then we describe each neuron by a single variable, scalar variable. And these functions are reduced to single variable real valued functions, A, B, and D. We write them in small case. And each matrix, Cij, is then just becomes a single numerical coefficient Cij. And we have the equations of motion of the Cohen-Grossberg model, which has this more familiar form. And if we want to see something even more familiar, I'm sorry, we have here the, I forgot, still the, this is the Lyapunov function of the Cohen-Grossberg model, and where the potential is obtained in this way. And you can represent the equations of motion in terms of the gradient of the Lyapunov or energy function. And these equations govern the dynamics of the network states, which are represented by the phase space variables, where here you have one variable for each neuron, one state variable for each neuron. And if we want to look at something more familiar, we have the Hopfield model, which is a particular realization of the Cohen-Grossberg model, where we have the AI are constant, the BI are linear, and the DI are actually what we call the activation function for the neurons. And we have this familiar equation of the Hopfield continuous neural network model for associative memories. So our model includes these important models as particular cases. And well, this is just a review of what I've said. We investigated extensions of the structural scheme for associative memory neural networks to more general settings where the neurons are described by multidimensional dissipative dynamical systems. We advanced a coupling scheme for dissipative units that leads to dynamical features akin to those required by when modeling associative memory. The family of neural networks we have proposed admits an energy or a Lyapunov function such that the network always evolves downhill in the energy landscape. And this is very important for associative memory. And our general scheme includes the particular instances of the Cohen-Grossberg and the continuous version of the Hopfield model. And I finished. I like to put the citation in my talk because I like to believe that I'm working within this context, which I think is very scientifically important, and like we feel like yeah. As biologists come to focus more of their efforts on the brain-mind, most of them have become convinced that the mind will be to the biology of the 21st century what the gene has been to the biology of the 20th century. Thus, François Jacot, in 1998, writes, "The century that is ending has been preoccupied with nucleic acids and proteins. The next one will concentrate on memory and desire. Will it be able to answer the questions they pose?" And this is a very interesting quote because it's written by Eric Kandel, who was a Nobel Prize in Physiology and Medicine in this book. And he quotes another Nobel Prize who was François Jacot. And I think this is very important because often we think that maybe psychology and is not such a hard science, but I think it's very clear that although it's very difficult to approach these problems, it's important that we approach them. And Kandel himself started as psychologist in Vienna, and then he became a very important neurophysiologist. So I think it's a nice problem too. Thank you.
Thank you, Roseli. Question, comments?
Thank you, Rosalie. Just a question. In your model, multidimensional model, you have different dimensionality for different neurons. Is correct? What is the motivation on this choice? Because one could expect that you increase the dimensionality, but for the neurons at the same time, same dimensionality.
We just wanted to make a very general model. Of course, in most neuronal systems, neurons are very similar. In our brains, the neurons are not all the same. They're not all the same, but they're very similar. And I think even Angel was reading some work that there's some speculation that even if there should be intelligent life, I mean, he read something that even if there's intelligent life, extraterrestrial, probably neurons in this kind of lives will be similar also. So this would be an argument that why do you need different dimensionalities? Because although they are similar, they're not necessarily the same. And also, maybe this kind of model can be applied to other biological systems also. So it's just to be general. Yeah.
It's just a question to animate the hard work we have after this session. Just to animate.
Oh,
No,
okay.
I just want to know what is for you the future of psychoanalysis. And what do you think about the book of Pasternak?
Of who?
This lady who
Pasternak.
wrote Pasternak.
I didn't read her book.
You
but
didn't read, but you
I heard
heard
about
the comments. So.
Yeah. I think there's a lot of maybe lacking information, because when we treat in different areas, it's and our first impression about some other area may be not so complete. And from what I heard about what she said, I think maybe if she read a little bit deeper into Freud's work, she might have a different opinion. Yeah, but I think so. Yeah, and also, I mean, this. Even before I started working on this, I saw a future because I had personal experience, and I read and I started going to seminars. And when I read the description of the neurosis by Freud, it's very clear. It's associative memory. So even if we don't know the real mechanics that's happening in the brain, but we can understand with these kind of models some kind of emergent behavior. I mean, it's exactly the same of what we call associative memory. If you read Freud's description, it's just associative memory. So I think that if you look more carefully, sometimes you can perceive things, but it's not very easy, because when you're working in different areas, I mean, for example, for me, it's not very easy to understand all the work that's presented here. Right? I mean, so you have to study.
Rosalie,
Yeah.
if you are telling a story to somebody and then suddenly you don't remember something,
yeah,
and you stop, and 10 minutes later you remember the name and you continue the story. This interruption, could it be a sort of failure of your downhill requirement?
It can be related to your theory, because what you have is you have a lot of noise in the system, and so the system fluctuates all the time. So the dynamics goes that at some point you may access something, and at another situation you lose it, because there's a lot of noise. I mean, I'm not a neuroscientist, But from what I've read, noise is very important in neuromodulators, neurotransmitters. So it's not, it's difficult to describe it in a deterministic way. Yeah, so that's why we use, that was the inspiration to use the models based on temperature, right? In our models, we use temperature and now the Q to describe noise in the system. Yeah. So I think that's why sometimes you remember, sometimes you don't. There are fluctuations.
In fact, it's a comment. A long time ago, I was a student, a graduate student, and I was to São Paulo in the retirement of a great physicist, Professor Mário Schoenberg. And I was in an audience, and people asked him what will be the future of physics. And he says exactly this. Yeah. One of the main points will be the study of the conscientials and the psychology and things like that.
Yeah.
Evaldo?
Thank you, Roseli. In your model, the matrix Cij is the connection between the neurons. In the Hopf field, you include the memories in this matrix.
Yeah. Yeah.
And here, how the memories are included?
We did it. It's you can use the Hebbian learning. You can use it, yeah, but it's a parameter that you, depending on what you're modeling, you can adjust it. In our case, we assume that it's constant, that it doesn't depend on the network state. Yeah, but you can use things like the Hebbian rule that you use in, yeah. But it depends on what the dimensions of your state variables are representing. For example, if you want to represent, like in spiking neural networks, where you want to represent, besides the activation, you want to represent frequency, spiking frequency, then, yeah.
Thank you. Any other question or comments? Let us, oh, I'm sorry.
So thank you very much for an interesting talk, but I do have a couple of questions, although things went quite, anyways, like if I go back to mathematics, so it's quite hard for me to understand. So how do you really map these things? So from which space to which space? And then also I couldn't understand.
From which?
I couldn't understand how do you define your functions from which space to which space? So there is like a mathematical, some mystery for me. Plus, I also couldn't understand the definition of this network, actually, the interaction function or interaction structure. Because if you do define this like a constant and so on, and it's like a Laplacian matrix, for instance, for a network, whatever your intrinsic dynamics, then system will be dissipative anyway. So it will basically lose all the Hamiltonian property, right? So maybe we can go back to this mathematical part and try to understand a little bit more, since it's a little bit mysterious to me.
Okay. Do we have time or? We can discuss later. Yeah. Okay. Mm-hmm.
I think so.
I think
because of the hard work.
Yeah. I can make an analogy with the Hopfield model if you want, and maybe it will be a little bit clearer. Yeah. Mm-hmm.
Okay. Thank you, Roseli, very much. So let us go to the same place of coffee break to cocktail.